adversary is trying to do, anything below below this line, in this particular example, is good instance. Anything above this line is bad instance. So now look what adversary has figured out what we are up to. So it's pushing its bad instances below the boundary line. So we won't catch it. 1, 2, 3, 4, 5 bad people. And we haven't caught. But we have caught all of these criminals, the bad guys, but we haven't caught them. So even one person we don't catch, they could come and kill you or something, right, in the real life. But in the malware, this is also real life. Malware, they could come and cause a lot of damage. So what do we do here? So this is, so one thing I've got, please excuse that, I've reversed it here, right? The green circles are good instances, the red crosses are bad instances. Whereas here I said what is below the line is good and above the line is bad. So I just reversed it. It doesn't matter. Main thing is the green is good, the red cross is bad, and this dotted line here was our support vector machine boundary. Anything below that is bad, above that is good. But what is the adversary doing? Trying to push this above the line. So you can see here, right? It's trying to push, a lot of the black squares are the bad guys trying to get pushed, right, into the good side. And this is the original support vector machine line. So what is the threat model? Attacker can modify X to X prime, modify packet length, add good words to spam. But the main point here is what we have to do with lot of mathematical calculations. So you need to have, you need to have very good mathematics, understand very good mathematics to do this, right? So, and especially, younger researchers and professors, they are really very good in mathematics. And so it's playing these games, and we've got to learn where toward the adversary. So adversary now thinks this is a boundary line. But with all the mathematics, we compute, we make the boundary line, blue line here, push it. So that is now our new boundary line, which means all these bad things here, right? All these bad things here will be caught because we have moved it. So now after a little while, adversary will try to figure out where is our line and know that we have moved it. So we have to figure out something and move it even further. But again, how far can we move? Right? We can move this right up to here. But then all the good guys will become bad guys. So we have to be very careful. We don't want false positives and we don't want false negatives either. We don't want the bad people to become good people and good people to be known as, to be caught as bad people. So that's where it's very challenging. So this is some of our work on integrating AI, AI, data science, big data, and so on with cybersecurity. Okay. Next, what I'm going to talk about, how do we apply all of these things to the cloud? Okay. So now, second part, as I said, of my talk is policy-based information sharing. So sharing information is just so important now. We are living in a world. Again, I am using the word data and information interchangeably. Okay? So data is, it could be, some raw bits of data, things like names and strings and so on. Information is what you get out of the data. But I'm not trying to, differentiate, just data and information. Okay. So policy and incent. So what I'm trying to say is this information we have to share in this world, right? Because we are not living alone. There's so much information sharing that has to happen between hospitals and your primary care physician and with the specialists and with your insurance companies. Imagine the amount of information being shared, right? The primary care physician will have to maybe talk to your cardiologist and send some information. Cardiologist will talk to somebody else. And so, but we don't want to share everything to everyone. Some things are not, only if there's a need to know. You don't have to share everything, say, with your insurance company, right? So there are policies and we also want incentives. Some people are very reluctant to share. So, but we need to share. If my primary care doctor is not going to talk to my cardiologist or cardiologist not to my primary care, there is a problem. So we have to give incentives in the sense that if the doctors don't share, then they have to be, told you better share, otherwise, you might lose your job. So, policy and incentive-based information sharing. So, initially our work, we integrated Medicaid claims data and mine the data. So, we enforce policies and determine how much information is lost, because we did some experiment by not sharing. Remember, some people still are very reluctant to share, right? The younger people are more willing these days to share, but the older people like myself are more sort of reluctant, and people even older to me, they don't want to share anything, right? So by not sharing, actually, we are losing out. So that's what we did initially. And I'm going to come up with this, okay? So we look at the incentives and risks for information sharing, because they are very frightened to share their information. Then, second thing what we did was we applied game theory and probing, as I mentioned in the previous charts. And so we want to find out, in this world, we have to, some partners are trustworthy, but still we don't want to share everything to trustworthy partners. We know that US and UK and Australia and New Zealand and Canada, they are all kind of very sort of countries that are very friendly to each other, but that doesn't mean everybody shares everything. But then there are some other countries or people, like there are some people in my team I'm close to, so I share more information. Some people that I'm not as close to, I share less information, but I'd like to get information about them, right? So that's sort of the second. The third category is that we don't trust each other at all, but we still have to work together. And so essentially we have to watch our back, right? So in my team, so I focused on this, and two of my colleagues focused on the other aspects. So I'm going to continue with the information sharing, right? So policy and incentive based. So we implemented a system without the cloud where we have all these databases, and each database, each organization, every organization, like my doctor's office and the hospitals and insurance companies, they have policies, right? So I share so much with my doctors. If I'm a primary care physician, I share so much with the hospital and so much information with the insurance company. Okay, so we had a lot of Medicaid claims data. It's a particular older people. No, Medicaid is people who cannot afford. They go on Medicaid. So we enforced policies. We implemented XACML, Extensible Access Control Markup Language, as a policy engine. And we showed how by not sharing, we can lose some information. By sharing, how much more, what are the risks in sharing? So we demonstrated. Then we implemented this in the cloud, because, you can keep individual databases and you can share the information, but, there is a problem in the sense that each one is holding on to information. There is no common place. So what we do with the cloud is everybody puts in their data and their policies in the cloud, and the cloud is doing all the work. It's much easier. So my doctor's office is going to put all the stuff in the cloud. My hospitals could be all over, right? All over the country could be sharing information and in the cloud. So for that, we had to develop a secure cloud. So, but of course, today, I will tell you, we could also implement this using blockchain in addition to this. So we didn't focus on networks. We focused on virtual machine monitor, secure data storage, query processing, and the applications. This is the generic, and this is the technologies we used. And what is in pink, work that still needs to get done because the project is finished, but what is in blue are parts that we completed. Okay, so we take the secure cloud, and we want to enforce policies on this cloud, so that's this part here, so that people can share data. So information sharing, access control policies, privacy policies, governance policies, integrity, data quality policies, so a lot of policies. And so, example, information sharing, like agency one. So let's say UK wants to share something with US, but UK tells US, I will share with you, but don't share with Canada, because maybe UK has some issue with Canada. And so when UK wants to share something with, if US asks UK, share something, UK will ask, why do you need it? Justify. Or, so UK will tell US, I will share with you provided you share something with me. Okay, so these are the type of policies, but I have to tell you, these policies are like children, TOY policies, because we are not policy people. So we have to work with policy people. So now we are working with the top policy expert in our university. She's the dean of policy school. And so now we are working, having more realistic policies. So how did we share? So we built a cloud with the Hadoop MapReduce. We can use different technologies. We use Hadoop MapReduce. And query rewriting. So research is how do you rewrite the query according to the policies and optimize. So we did 2 prototypes, relational data, secure query processing with Hive system, relational, and RDF data, semantic web data for videos and images. We used another system called Sparkle. Okay, Sparkle is a query language for semantic web data. And we demonstrated with XACML. Now, the interesting part is joint demonstration. We demonstrated with King's College, University of London, and Italy. So, US Air Force funded us, and US Air Force is also, as London, they fund projects in Europe and Africa. And there is an office in Tokyo, they fund projects in all of Asia and Asia Pacific and Australia. Asia and Australia. So even India, you could maybe write to them and, to have some kind of a project. They provide funding. So we had 2 demos, and one is with cloud only in Texas, and the second demo cloud is we had multiple clouds. Cloud could be in Texas, cloud could be in London, cloud could be in Insubria is near Milan, Italy. Okay. So the first system, what did we do? Very briefly, because I want to make sure I cover everything. So we have Hadoop file system, on top of that Hive. So we secure all of this, right? We have secured Hadoop, secured Hive, and then we build the XACML policy engine. Now Hive is relational database for the cloud, big data. It's a big database. And so the XACML policy engine, this is our demos. Okay. This is our first system, okay? And then the second system, what we did was, okay, this was great. Relational systems, XACML, and Hadoop. But we found that performance was really bad because we are mixing and matching technologies. This is relational. This is based on XML. So what we did, okay, so the second thing we did was, let's use Sparkle, for maps and geographical information, images. So we figured that semantic web data, like RDF data representation, XML, would be better. So we did something very similar. Only problem is we didn't have a Hive equivalent. Hive was developed by Facebook. We didn't have such a system. So we had to develop this Hive equivalent for semantic web data. And then we had 2 demonstrations. The first demonstration, this is the first demonstration, where we used a Hive prototype and our Sparkle semantic web prototype, 3 agencies, Dallas, London, and Insubria, Italy, and they share information. We had the cloud in Dallas, everybody puts in their data and the policies in Dallas cloud, and we share information accordingly. If London asks Dallas, give us some information, I will tell them, I will give it to you, but don't give it to Milan, Italy. Okay, things like that. But this is where we found that the performance was not so good, right? Because we are mixing and matching. Here we have relational data and XML. Here we have RDF data and the policy is XML. So we are mixing and matching. So we said, why not do everything in RDF? Right, our policy, our data engine. So we have 2 components, data engine, policy engine. Why don't we have RDF for everything? So we had to now go and develop a policy engine. Fortunately, under a separate project, we had a policy engine with RDF, but not on the cloud. Okay, we had a standalone policy engine working with RDF data. But this was not on the cloud. So we had to re-implement this whole thing. I won't say port, P-O-R-T, because it's not just a matter of taking it and putting it in the cloud. We had to re-implement everything. And so we had to re-implement the policy engine in the cloud. And I don't want to go into the details, but we have a number of papers. And now we are sharing information. The cloud could be anywhere. Everything is in RDF. What I'm trying to say is that when you work with one type of data, not mix and match like relational and XML or RDF and XML, if you do everything in one language, then there is less impedance mismatch, meaning we don't have to be doing all these translations. So now we had London, US, Italy, we had very good performance. Okay, so that was information sharing. Okay. So we also did very briefly some additional things like storing the data, right, in a hybrid cloud. What is hybrid cloud? One is public cloud, one is private cloud. Companies may want to use private cloud for sensitive information. And the public cloud, because public cloud like Amazon, AWS is already available, and so we can use the public cloud to share the data. Okay? And the private cloud is for all our sensitive stuff. And so the challenge is what data goes into the public cloud, what data goes into the private cloud. Okay, so we had to do a lot of analysis. So data for us here was relational, we used sort of some kind of a relational data. And so based on, remember our objectives, it has to be cost effective. So cost and security privacy risks and utility. Based on that, we decided what data goes into the public cloud and what data goes into the private cloud. So that's this experiment. We also did forensics work, like, where do you put the malware, the antivirus software, right? Do we put this in the virtualization hypervisor that is monitoring all the guest operating systems and the host operating system, or do we put it in each of these operating systems? So some trade-off experiments, and I won't go into these details, okay? Okay, now we are saying, okay, all this time we said, okay, secure cloud, how do we exchange data and share? Now we are saying, okay, cloud is also very good for security applications. So earlier we said we are securing the cloud and we are doing some information sharing application. But cloud is also very good for security applications like malware. So what did we do? We have developed a number of malware detection algorithms. We took those algorithms and we re-implemented these algorithms in the cloud just to see better performance, because everybody says cloud is great, it's giving us very good performance, so why not validate? So we took some of our algorithms and please note, re-implement them in the cloud, and yes, it gave us these machine learning algorithms and it gave us very good performance. So when we are using AI techniques and machine learning, it is very time consuming, but use the cloud, but the cloud has to be secure. What's the point in using a cloud that is not secure for security applications? And of course, another thing that we have to be, and I'm going to very skip, is the cloud governance, because these days governance is becoming so important. Whatever organization, right? You have to have proper procedures. So whether you are doing a computer system or a network or whatever, you need to have proper procedures to make sure that everything is in order. So when you are using the cloud, you have to make sure cloud is installed properly, cloud is secure, and all of that stuff. So the question I'm asking here, whose responsibility is, right? Is the, Chief Information Security Officer? Is it the Chief Information Officer? Who is responsible for the cloud? Because organizations are more and more migrating to the cloud. Or is it the Chief Cloud Officer? So do we need a Chief Cloud Officer? And again, you can have so many types of officers. So the organization has to limit. Now, very big companies, right? A company like, Microsoft or IBM and Apple and so on, they can afford to have many of these officers. So smaller companies have to decide how many officers they want. So that whole thing, we don't study in computer science, but business school studies that. Okay. So the last part of my presentation, I think I've got, the timing is now, so I've got I'm going to try this, finish in about 5 minutes, because I was given 40 minutes for the presentation. So it's about 9:33 now. And I don't want to delay because the next speaker, a very, very brilliant lady, is going to speak next. So I want to make sure I finish before that. So now from cloud, we go to social media, to IoT. How do we do it? So Internet of Things, Internet of Transportation. Cars are talking to the trucks, talking to the trains. Here we have Internet of Home Things, right? Internet of Things like our coffee maker, tea maker, talking to the clock and talking to various other things. The cars and the trains and the trucks and so on, all talking to each other. Okay? So security and privacy for cloud-based Internet of Things. So a lot of mobile devices all over the place, 1 billion smartphones, ever increasing popularity, right, in smartphone applications. Recently, there is something called quantified self, where psychologists and sociologists are trying to get as much information about us as possible and to help us, because I really like vanilla ice cream and milk chocolates. But I know that's very bad for the health. So I don't keep anything at home, all right? But imagine if I have all this, open the refrigerator and find all these chocolates and I start eating. It'll be great if somebody can tell me, right, no, you should not be eating that. In fact, today I was at work. I had some meetings, some panel meetings. And so I forgot to bring my lunch. So guess what I do? I go to the vending machine and I take a milk chocolate. Very bad. But at least it's once in a way. Imagine if I have it at home, I will eat it every time. Okay. So because of that, my privacy, on the one hand, it's good that it's telling me, no, don't eat chocolate. It would have been very good for the vending machine to tell me, do not eat it. Okay. But the vending machine didn't. It will be really great. Information is gathered and it's told to me so I can decide. On the other hand, my privacy is violated because somebody could take that information about me, collect it and send it to my insurance company. Insurance company is saying, oh my God, this woman is eating chocolates. And in the future, fortunately, I don't have diabetes yet, but my father and mother both had diabetes. So in the future, if I get it, they may say, no, we are not going to treat you. So that's a problem. So I got to be careful. So, but okay, I know I have to be careful because I have to, preserve my health. But my privacy is violated. Right now, my concern is my privacy, right? So with a lot of mobile devices and quantified self-movement, a lot of information gathered for our good. But as a result, what I'm saying here, our privacy is violated because people can use it for bad purposes. And we have published a nice paper. So what we are saying is in our paper, right, is what we have developed a system is a lot of information, health, fitness, location, social media, all of this data is being collected. And so what we are saying, and then some of the data in the cloud, but what we are saying is policy. Remember, this whole thing is about policy. Policy has to govern everything. So when we collect data, when I come and ask you to give me information about you, I have to tell you why I'm collecting the data and how long will I be keeping the data. So policies have to govern data collection, data storage, data analytics, data sharing, and even data deleting. Once I delete the data, have I really deleted the data? Am I kind of taking it on the side and storing your data? Somebody has to come and audit me. So all of that is important, and this is what we designed and developed. Okay, so I'm essentially saying what we did here. Okay, lot of data being collected. So essentially, this part here is what I've said here. Okay, so I'm almost time. So all I'm saying is a lot of data is being collected, and we have developed such a system. Okay, so now for IoT, secure IoT design, right? We have Internet of Transportation. All these vehicles so this is Internet of Healthcare things. So here, all of the IoT systems, a lot of data is being collected, and we want to develop a model of the vehicle, and we have to look at offline pre-processing and online stage. So we still just implemented Kalman filter in this case, and detecting anomalies. Has our vehicle been attacked? Remember I said the other day I went on Uber, and I was a bit nervous. All these systems all these computers and microprocessors. What happens if my system is attacked? Okay, so that's the solution. We developed a solution. And here is the implementation that we did with drones and with, aerial vehicle like drones and with cars. We implemented our design, for our vehicles, Internet of Vehicles in here. But what about privacy? Right? So just like we did that earlier case I said with our cell phone, we are collecting all the information. For our cars, we are collecting radar, GPS, camera, LIDAR, ultrasonic sensors, and all of this data being collected. It's encrypted. So policies have to govern. Policy must say how we collect data, right? In the Internet of Transportation. How do we store the data? How do we analyze the data? So policies have to govern. Okay. There's also social IoT, vehicular IoT. So in social media, right, our vehicular networks are all going and they are communicating with each other socially. What is the best route to take? Or is there a restaurant I can go and eat? I'm in this location. But again, imagine we give all this information, our privacy is getting violated. So I took this information from this paper. Very nice paper they have written. And again, for vehicular IoT, remember information sharing framework I explained earlier? How can we apply that framework, a cloud-based framework, in this environment? So AV1, we can have 1 car, 2 cars, 3 cars, all sharing information, things like, which routes to take, is there a restaurant, is there a hotel nearby, I'm stranded, what do I do? But again, we have to be very careful by giving, because these are strangers we are talking to, right? So again, privacy. So my last chart is, I'm sorry, I'm going a little bit over. I was told to stop at 9:40. So development in integrating cybersecurity. We talked about AI for insider threat, AI for cybersecurity applications and attacks to AI, some privacy aware stuff. And then we talked about Internet of Things. And again, as driverless cars becoming a reality, how can we apply secure AI, integrating secure and AI? How can we develop privacy-aware framework? Okay, numerous opportunities, and we have substantial research. And I see that we have other distinguished speaker. She's really a brilliant professor from MIT. So sorry that I took a little bit of her time. And so this finishes my presentation. And Professor, I'm going to stop sharing the screen, okay?
Yes, ma'am, yes.
And yeah, I've stopped on the dot at your time, 9:40, I think, yeah.
Yeah. So, is that?
Yeah, because I don't want to take the time of, Professor Medard. So maybe they could email me the questions or whatever, Professor, okay?
Okay. So Professor Muriel Medard is waiting.
I think Professor Medard is here. I'm so honored to meet you, Professor Medard. I've heard so much about you.
Okay. So let us give a good applause to Professor Bhavani Duresingam, and we will keep in touch with her. And please send your questions to her. I will share the email ID with you. Thank you, Professor. Thank you.
Thank you. I'll stay for a few minutes and then I'll leave, okay? Thank you.
Thank you. So if your time permits, you can also listen to our Professor Muriel Medard's lecture. Yeah, thank you. Hello, welcome Professor Muriel Medard. This is Professor Yagya Narayanan, organizing chair here. So we are very much honored to have your invited talk here for this session. So we warmly welcome you. Just allow me to briefly introduce you to the audience. Ladies and gentlemen, esteemed participants, it is my pleasure to introduce our distinguished resource person for today's event, Dr. Muriel Medard. She is a prominent figure in the field of software engineering and science, currently holding prestigious position of NEC professor at the Electrical Engineering and Department of MIT, prestigious MIT. Dr. Medard is widely recognized for her groundbreaking contributions to the field of network coding and reliable communications. So as the leader of the Network Coding and Reliable Communications Group in the Research Laboratory for Electronics at MIT, she has spearheaded numerous research initiatives and made significant advancements in the field. Dr. Medard is the chief scientist for Steinwolf, a company she founded. Her entrepreneurship and commitment to technology transfer have been instrumental in the success of Steinwolf and Codon, another venture where she provides her valuable consultancy services. Dr. Medard's exceptional contributions to the field have garnered international recognition. She is a member of several prestigious academies, including the US National Academy of Engineering, German National Academy of Sciences, American Academy of Arts and Sciences, and a fellow of the Institute of Electrical and Electronics Engineers. Her peers have acknowledged her outstanding achievements by electing her as a fellow of US National Academy of Inventors. Give her a big applause. Throughout her illustrious career, Dr. Medard has received several numerous accolades and awards for her research and academic excellence. These include the Medard MIT Harold E. Egerton Faculty Achievement Award, the IEEE Communication Society Edwin Howard Armstrong Achievement Award, the IEEE Kobayashi Computers and Communications Award, and ACM SIG Communication Test of Time Paper Award, among many others. Dr. Medard's contributions extend beyond her research endeavors. She has been an active member of various technical program committees. She has served as chairs and also served in editorial boards for prestigious IEEE publications. Her commitment to mentoring and promoting diversity in the field is evident through her establishment of the Women in Information Theory Society with ITS and the Information Theory Society mentoring program. With over 60 patents to her name, Dr. Medard has made significant contributions to technology transfer and innovation. Her expertise and leadership have guided and inspired numerous master's students, doctoral students, and postdoctoral fellows whom she has supervised throughout her career. Today, we are very much honored to have Dr. Muriel Medard as our resource person and an elite invited talk speaker. Her vast knowledge, research accomplishments, and dedication to academic and technological advancement make her an invaluable asset to our event. So once again, give her a big applause and welcome her for her much awaited invited talk. I now hand over the session to Dr. Muriel Medard. Madam, please.
Thank you. Thank you very much for that very kind introduction. Thank you for inviting me. It's very late here, so I will sometimes speak a little to let my family sleep, but it's a pleasure to be able to share some of my work with you today. It's never just my work, of course. It's always a group effort with many of my collaborators, and I'm hoping that the topic will be motivating to many of the people listening, because I think it is timely. It's about standards, and standards have been very much in the news, particularly with 5G and people thinking about 6G. But how can we allow standards to allow innovation, and in particular the kind of mathematical innovation that the attendees and participants in this event are really dedicating their professional efforts to. So the title is Revisiting Standards to Allow Innovation. And before I run into what it means to allow innovation, let's spend a little time just seeing sort of where we're at in standards specifically for communications. And I would posit that if you look at standards for communications right now, you have what I often call sedimentary layers of different kinds of technologies, which are there really because of decisions that were made some time back. Sometimes those decisions were the appropriate ones in the context. Sometimes they maybe were not necessarily the right engineering decision, but they take a life of their own. And these sedimentary layers just keep piling on top of each other, and making a more and more heavy, unwieldy, and intrinsically poorly designed system. Now, if we want to try to make sense of these different components, maybe it makes sense for us to really think of them in terms of groups. So, if you will, sort of what we're doing here is we're grouping it into a taxonomy where in light blue here we see everything that deals with dealing with erasures, with losses. And those losses are basically when errors cannot be recovered. So the errors are showing here in turquoise. And then you have everything that has to deal with trying to then take the bits into a format that's ready to be transmitted along whatever the actual physical medium happens to be. So let's think of all of the interleaving, interference management, all of that sort of trying to massage bits before they're actually transmitted. And then you have the actual transmission with the modulation of the transmitter receiver. This is the basic taxonomy that we're going to use. And this taxonomy of, dealing with erasures, dealing with errors, dealing with managing the access to the medium, and then dealing with the actual transmission, I think is a fairly reasonable way to chop things up. Now, how are we actually dealing currently with aspects such as erasure? We generally deal with it right now through very degenerate modes. And what I mean by degenerate means that, they're artificially limited relative to what they could do. So let's look here at acknowledgements and retransmissions, where an ACK means that a packet or a frame, as we may, depending on exactly which layer we're working at, would be received or not received, and a NAC means that the reception was not successful. So basically, let's think of time as being along the different rows. So these matrices indicate what the transmission along a time indicated, let's say in slotted time, along the different rows. And then let's look at the columns as representing the packets, the payload packets. So current systems use a degenerate system in the sense that these matrices only have on each row a single entry. So a single entry means that at time 1 you send packet 1, at time 2 you send packet 2. Packet 3 in this case doesn't get received. There's of course a delay in the transmission between packet 1 at time 1 and the reception, which is shown here at time 3. And then when packet 3 is not received, you see a negative acknowledgement for packet 3, which is happening here at time 7, and that then induces the retransmission of packet 3. There's no reason when you think mathematically of these transmissions in terms of these matrices, where again the rows represent time and the columns represent packets, there's no reason why the matrix should have this degenerate form. In particular, you can imagine still sending packet 1 at time 1, as you see on the right-hand side, but at time 2, sending a linear combination of packets 1 and 2. So that's what those two dots mean. It means that both packets 1 and 2 were components in the transmission at time 2. Of course, this transmission does not take any more bits than sending a single packet. It just means that we're sending packets which are bitwise or bytewise or somehow symbol-wise combinations of the original payload packets. So if you see here the same pattern of losses, and FEC here stands for forward erasure correction. What you see here is that you can be acknowledgement, not just packets, but you can acknowledge also combinations of packets. And what happens here then is, by the time you look, for instance, at time, say, 9, on the left-hand side with the degenerate approach, only packet 3 has been received, whereas at time 9 on the right-hand side with a more flexible approach that allows not just a single non-zero entry per row, you end up with packets 1 through 5 having been received. So this benefit means that you get packets delivered in a more not in a more reliable but also faster, lower latency approach. You're both increasing throughput and reducing delay. What does this mean in practice? Let me give you an example here with the RAMP product by Steinwolf. These are experiments that were done in close collaboration with Red Hat. So RAMP does something which is fairly similar to what I just showed you in terms of combining coding with transmission. And what you can see here is if you run a fairly standard test for performance of networks called iPerf, is that you can see that you have 100-fold improvement in throughput. And if you look at the jitter, that is to say, the uncertainty, here it's HTML speed test, you're doing a ping, you can see that the jitter is also improved by many orders of magnitude. And it means that you can do this you can improve the behavior of networks by using the sort of coding scheme that I showed. Randomly network coding is a method that was developed in my lab. And what that does is, as you see here with the adaptive random linear coding, is that the actual choice of the coefficients for the contributions of those different original packets is chosen in a very flexible fashion. The reason why it's important that they be chosen in a very flexible fashion is there are too many different possibilities. Indeed, there's an infinite number, growing number of possibilities, and therefore a structured code such as, for instance, codes like Luby transform codes or so on are simply not suitable, not feasible. So if we look at the kinds of systems that are out there right now for managing losses, you have systems called ARQ for which do automatic retransmissions, hybrid ARQ which combine error correction, which we'll touch upon next, and retransmission. And what we can show is that by doing something similar to what I showed you before, you should actually be able to do much better. And this is actually compatible with 5G, and we have ongoing work currently in my lab with JMA Wireless to reduce the number of retransmissions and speed up delivery, improve throughput by in effect tweaking the current standards. Now, the thing to think about here is that this tweaking of standards is something that we're basically doing post facto. It, of course, would be far more preferable if, rather than having those very inflexible standards with those, many sedimentary layers, we were instead able to have a single unit with an input and output, an API in effect, where inside that API, which would be just a single system that managed a single system that was able to manage losses, we were able to innovate inside that system. If you're interested in the types of network coding techniques I just mentioned, let me make a shameless plug for our book, Network Coding for Engineers, which will be coming out this year, co-written with Dr. Vasudevan, Dr. Peterson, and Professor Duffy. And it will be coming out in IEEE Press. Okay, so what I'm hoping to argue here is that rather than having, again, all these different units, which are at this point very suboptimal, we might think of really having a single unit which manages erasures. And the erasures happen, in effect, because often there's been, of course, in some cases it's congestion and so on, but generally there's been a failure of delivery because of a failure of error correction. So let's go to the next layer, which is the error correction. Currently, there are multiple error correcting codes, which we show here as code 1, code 3, code etc. And a pile of chips here represents the fact that these different encoders require different decoders. You have a large number of possible encoders and decoders, but the rule of thumb is that generally decoders are specific for particular codes. You have things like cyclic redundancy check codes, which are usually only used for error detection, Reed-Muller codes, which have a majority logic decoding, Boas-Chaudhary-Hockenheim codes, which go with the Burley-Camp-Massey, CRC-aided polar codes, so-called CA polar codes, which go with CRC-aided successive cancellation list decoder, and random linear codes, where the encoding matrix is random, no matter, akin to what we just discussed previously. Those are known to be theoretically optimum in many ways, but for instance, up until now had no decoders. Because of the fact that the decoder is currently tightly matched to the encoder, the standardization bodies have gone and picked certain codes. 5G, for example, has LDPCs. The LDPCs are so-called modern codes, but they date back to the 1960s. They were actually the doctoral thesis of my doctoral advisor, Bob Gallagher. The CA Polar codes came out in 2010. It's really a extension of Polar codes, which were invented at the end of the 2000s by another student, Bob Gallagher, Erdal Arakan, who is a faculty at Bilkent University. What we have developed with Ken Duffy from Northeastern University, my co-author, whom I just mentioned on the previous upcoming book, is guessing random additive noise decoding, which shortens pleasingly to GRAND. What you see there is the first chip, first GRAND chip. And if you're interested in GRAND, I would encourage you to look at our website, granddecoder.mit.edu, where you can find tutorials, papers, as well as some MATLAB code to run GRAND. GRAND is optimally accurate decoding, and it is universal. It actually does not care about the kind of code that is used. And the way it operates is that rather than operating like traditional decoders, which use the structure of the code in order to try to reconstruct the original transmission post errors. And of course, errors are very different from erasures. When we were looking at the matrix before for erasures, the decoding was very, very simple because basically an erasure just meant that there was a missing row. So all you needed in order to decode was to do a matrix inversion. And the matrix inversion here was very simple because we're talking about extremely sparse matrices. So erasure decoding is actually entirely trivial. It just requires inversion of a matrix. Error correction, however, is different because rather than having missing rows and just having to accumulate more rows, the rows are themselves erroneous. And of course, we don't know what the errors are. So the way GRANT works is that it guesses the effect of the noise, not the noise itself, which may be continuous and of course difficult to guess, but the effect of the noise, which that effect is digital, from most likely to least likely. There's flexibility there with a little bit mismatch. It's not a big deal. And then the first time that we invert the noise effect and find an element of the codebook, that is the maximum likelihood code. So in particular, what this shows is that if you look at, say, capacity here, it's dashed lines. Here we see a binary symmetric channel, one of our canonical channels, which we work with P, little p being the probability of a bit flip of 10 to the minus 2 and 10 to the minus 3 on the left and right, respectively, and a target block error rate that's, say, small frame decoding error of, say, 10 to the minus 1, 10 to the minus 3. The idea that, the raw bit error target block error rate are about the same is, not a bad rule of thumb. What would happen, of course, if you send 100 bits and your probability of having a bit be wrong is 10 to the minus 2, the probability of that block of 100 bits showed last year at ISSCC, which is one of the two top conferences in circuits and integrated circuits. You can see that we are able to outperform by well over an order of magnitude the best fabricated systems, and we're able to outperform with a fabricated system even the simulated, emulated systems. Emulated systems are always more efficient than taped out systems because, of course, you don't have the issues of imperfections and things such as, clock slippage and so on, the state of the art, even emulated systems, used our algorithm GRAND with a modification for soft information, which uses ordered reliability. The reliability is given as shown on the left, usually by the log of the likelihood ratio, where if you think of transmitting those 4 different points that you see in the complex plane is being used to represent electromagnetic transmissions here. So we have an imaginary signal and a real signal, what's usually called the in phase for the real and the quadrature for the imaginary in the parlance of communications. What you see here is that, receptions that are signals that are received that are close to the border of the region between two points that were sent are not don't have a high likelihood, are not very certain or confident. And then, of course, if you are only if you're close to only really one point, then the likelihood goes up in those warmer colors. So by ordering these different reliabilities, we are able to look at the likelihood of an entire noise effect. Remember the noise effect we spoke about in the last slide, and therefore ORGRAND is now the state of the art. Interestingly enough, the performance we can show does not depend on the code. You can see here for different kinds of codes. The codes all do pretty much the same, whether it be a CA Polo code, which I mentioned before, a random linear code, a CRC, which I mentioned before, is generally up until now has not been really used for wire error correction, just error detection. We can use it for correction. We can even use encryption schemes such as AES. We can use polarization assisted codes, which is some very recent codes. And you can see just the current state of the art, which we show here in green for CASCL. Which I mentioned before, we outperform it significantly. If you think of whether you might want to use maybe, say, machine learning to construct the codes and construct the decoders, that has been an area that people have spent a lot of effort on recently. On the decoder, there's no point because our decoder is already basically optimum, and probably so. So maybe you could try to think of whether it might be worthwhile to choose machine learning techniques to design the encoder. But as was shown by the group of Batsuka steaming here down in the right, you can see that actually choosing a random code and choosing the state-of-the-art machine learning gives you the same performance. So this is not an area where using machine learning is going to advance matters. Simply because the optimum is quite feasible. So there's no need to go looking with complicated optimization techniques. FER here for error rate is equivalent to block error rate. The curves here, just for reference, the abscissa is called EB over N0, which is the energy per bit over N0, power spectral density of the noise, generally assumed to be added wire gaps to noise. And the abscissa is shown in dB, so 10 log 10. It's a logarithmic scale. And the ordinate is also shown in a logarithmic scale, but in just base 10 here. The decoding time also does not really matter. It's not really. It doesn't really depend on the kind of code. You see that on the bottom left-hand side, where simple geometric approximation shows the behavior almost perfectly for any kind of code. Interestingly enough, for long codes, the LDPCs that I have mentioned before, you can go back to very old codes, product codes. Product codes were developed in the 1950s by Peter Elias, who was actually also in the family tree, if you will, because he was the advisor of Bob Gallagher. And as I mentioned before, LDPCs which were from the 60s, developed by Bob Gallagher, have been up until now the state of the art. And with these simple product codes from the 50s, so even earlier than LDPCs, by applying grant appropriately, we are able to outperform LDPCs. So the idea here is that I think in order to allow innovation of the kind we just saw, rather than having monolithic encoders, decoders, and deciding to do LDPCs or CA Polo codes, say in the 5G, I believe in the future, in order to enable better performance, we'll have general encoding units and decoding units that just tell each other how they're encoding, and the decoding will use only grant. Going on further in the system, if you look now at issues of interference management, interleaving, and so on, again, as I mentioned, many of these elements may have been a good idea at the time, but many of them remain there without really consideration as to whether their purpose is no longer useful. Let me start with interleaving. In interleaving, data is collected as rows, it's transmitted as columns. The idea is to make the noise, which generally has some structure and correlation, as you can see here on the left. This is data from Wi-Fi systems. Before interleaving, you can see this sort of clumping of noise. After interleaving, it looks independent. Traditional decoders, such as CRC-aided successive cancellation list decoders, do worse. Again, with this figure of merit of EB over N0. Just to be clear, so CB is the energy per bit. It subsumes both the energy in terms of joules transmitted per bit. It also subsumes that N minus K I spoke about before. So it subsumes the energy of those so-called redundant bits. If you look at the correlation, so rho means a higher correlation. As you can see, again, on the left, correlation tends to be high. If you think of having a higher rho, traditional decoders work worse with higher correlation, which is why the interleavers are there. However, interleavers are intrinsically a poor idea if you think of them theoretically, because the entropy of the noise is actually increased by having interleavers. Grant, on the other hand, can make use of any sort of statistical structure in order to reduce the number of guesses, or in effect, in order to be able to take active benefit from the structure of the noise, and therefore we're able to get the same benefit with, say, a rate at the same EB over N0. We can have rates of 0.9 and above, rather than the current rates, say, of 1/2 that people are using, which means that right now, the interleaving and the use of legacy, highly suboptimal decoders is literally wasting half of the resources in the current systems. Without going to other aspects of access, multiple access, let me just briefly touch on basically the premise here, which is that we in order again to allow innovation, I'm hoping that current approaches will be set aside, and instead we'll have a general interference management unit, which includes the interleaving, and that those interference management units will be able to actually make better use of the resources in the way that we saw. Finally, I'm going to argue, without going into as many details, that rather than having some of the traditional modulation, we should be able to allow optimal modulation and demodulation, where again we get very considerable gains from that. Optimal modulations don't look like those 4 points I showed you before with equal probability in transmission. Instead, they look very irregular with different probabilities also of transmission of different points. And you can see here that the losses and again the considerable waste of resources currently, in terms of energy, time, bandwidth, etc. That arises because of using traditional modulation versus optimal modulation is really quite visible. Okay, so I hope I made a case here for modularity. Modularity is a way of getting around the standards which currently lead to very costly inefficiencies. And complexity requires modularity to enable compatibility with adaptability. And I hope that the role of standards is going to move to creating APIs, which allow robustness, as we know from the software world, but do not require the kinds of monolithic systems that are currently in place. And with that, I'll take any questions if there are any, and I thank you for your attention.
Yeah, that was
Hello.
That was a very good talk, and it's not really my area, but I learned a lot from this talk.
Thank you.
It was very informative to me. So I don't think I can ask intelligent questions, but it was very, very. I really enjoy listening to your presentation. Thank you.
I appreciate it. Thank you very much.
Audience, is there any questions? Okay, if there are no questions, let us give a good applause for Professor Muriel Medard for her talk.
Not sure. Yes, I don't see anyone on the chat. But anyway, if people have any questions, I would very much welcome them. So feel free to email me. I'll pop my email in the chat.
I don't know if
happy to answer any questions.
Whether the organizers are here, I don't see, or maybe they are muted. Yeah.
I believe they're muted. Yeah.
Yeah.
Yeah, thank you very much, Professor. Hello, are you able to hear me? Thank you very much.
Again, I'd be happy to take questions through email. And it's late here, it's midnight, so I'm going to take my leave. And thank you again for inviting me.
Nice seeing you virtually. Bye.
Bye-bye.
Bye.
Okay, so the session has ended a few minutes before, I think. The session is supposed to complete at 10:40, but Professor has finished her talk 10 minutes before. So let us break and again reassemble at 10:40. at 11 o'clock. At 11 o'clock here for paper presentation session. Thank you very much.
The first presenter, Ram Kumar, can start.
Very good morning to one and all present here. Before starting my presentation, I would like to thank all the concerned persons of this conference, ICMC. I, Ram Kumar, a research scholar from Central University of Tamil Nadu, is going to present entitled Stabilize a Group of Set Ideals. The authors of this paper are myself and Dr. V. Renuka Devi, Central University of Tamil Nadu, Thiruvarur. So the outline of this presentation are abstract, introduction, preliminaries, and so on. So my abstract, we derive a necessary and sufficient condition for a isomorphism between stabilize a group of set ideals. Also, we proved that the outer automorphism group of the stabilizer group is a group of order at most 2 if it is isomorphic to its polar. In 1999, Miskin proved that a necessary and sufficient condition for the completeness of stabilizer group in terms of Lagrange ideals. Later in 2002, Miskin and Briakov found a necessary and condition for the same in terms of reflexive ideals. So motivated by this, we attempt to find a result connecting Lagrange ideals and reflexive ideals and some results. So in this paper, we try to prove these ideals for non-uniform ideals, notably top ideals. So as a basic definition for set ideal is a subcollection of power set of X. It has to satisfy two conditions. First one is it should be closed with respect to union. Second one, it should be closed with respect to intersection. These are all examples of set ideals. So in general, an ideal need not contain all the singleton subsets of X. Suppose if it contains all the singleton subsets of X, then the ideal is said to be an admissible ideal. And we know that symmetry group on X. So let X denote the symmetry group. Then the stabilizer group is nothing but set of all the bijective functions which is I invariant. So next definition for each infinite cardinal, the collection X less than lambda is nothing but the set of all subsets of X whose cardinality less than lambda will form an ideal. These ideals are referred as cardinal ideals. So throughout this section, I assume that an ideal I is an admissible ideal on X. So next definition, I am defining a norm for an ideal. A norm is nothing but it's a minimum of cardinality of sets whose sets are not in I. Next definition, height of an ideal, it should satisfy I less than the cardinal X less than lambda. I am collecting minimum among those collections. So for a non-proper ideal, we define height and norm is nothing but the next successor cardinal of cardinality of X. So there is a remark, the relation connecting norm I and the height of I, it should be always norm I less than or equal to height of I. The equality holds if and only if the ideal is an cardinal ideal. So an ideal is said to be full if it coincides norm with the cardinality of X and is said to be top if height of I equal to cardinality of X, the next successor cardinal of X. So there is a remark, suppose I is a top ideal, then it contains a moiety. Moiety is nothing but a subset of X in which its cardinal and its complement cardinality should be same. The next definition is the lambda polar of an ideal, and in particular if lambda is equal to norm I, it is defined as a polar of an ideal I. There is a remark connecting lambda, norm I and height of I. Next. So the lambda adjoint is nothing but the set of all subsets whose power set intersect with I equal to a set A less than lambda. There is a remark connecting norm I and lambda as usual. And there is a definition between isomorphism between two ideals. So two set ideals on two different sets X and Y said to be isomorphic if there is a bijection between the base set X to Y such that f of I equal to J. Next. So these are some important definition. An ideal is said to be lambda reflexive if the ideal is isomorphic to its adjoint intersection height of I, and the ideal is said to be Lagrange ideal if it is isomorphic to its polar. If it's I double pair equal to I, then ideal is said to be regular ideal. So it's clear that I pair is an regular ideal. And the definition for complete, a group is said to be complete if it has trivial center and all the automorphisms are inner automorphisms. So next we found that relation connecting Lagrange and reflexive ideals. So cardinal ideals, we saw that the cardinal ideals are neither reflexive as well as nor reflexive as well as nor Lagrange. And next example shows that a reflexive ideal need not be a Lagrange ideal. Next. So in such case, there is an ideal which satisfies both reflexive and Lagrange. One kind of example is that. And the next example shows that there exists an ideal which is neither reflexive nor Lagrange. Previously we saw that a cardinal ideal is neither Lagrange nor reflexive. This example is a non-cardinal ideal which is neither reflexive nor Lagrange. And there is a theorem, the relation connecting Lagrange and reflexive ideal. Every Lagrange ideal is reflexive. Converse need not be true. If the ideal is full, then converse also holds. So these are our main result. So if suppose the stabilizer group of two different ideals I and J are equal, or the next theorem are in the sense of isomorphic, then either the two ideals are same or else one is polar to another ideal, provided the excess condition. Next one. So in that above theorem, the ideal top cannot be dropped from the hypothesis. For example, if we consider the set of all finite subsets and the set of all countable subsets, both having same stabilizer group, but both ideals are not same and one is not equal to polar of another. Before sleep. So there is an example. This example shows that I found two different ideals I and J, but satisfying the condition J is not a subset of I where I intersection J is top, but I is not regular. Why I am saying this example means in 1999 Miskin proved that the result is true for a regular top ideal. We have imposed some conditions, so we showed that that condition does not imply the regularity. Next. So next there is a corollary. If I is a regular top ideal, then the converse. Previously we saw that a stabilizer group of two ideals are equal, then either the ideals are equal or one is polar of another. But this result shows that the converse part of that theorem. So in that theorem, the regular top condition cannot be dropped from the hypothesis. Next. So suppose I is a top ideal and the stabilizer group is complete, then I is not Lagrange ideal. This was proved by Miskin in 1999, and in 2002, Miskin and Briaco proved that the same condition, if that group is complete, then I is not a reflexive ideal. So this the next theorem, the partial converse of the above theorem, if I is a Lagrange ideal, then its outer automorphism group is a cyclic group of order at most 2. So conclusion of my presentation. In this article, we found a necessary and sufficient condition for isomorphism between two different set ideals. And also we study the completeness of the stabilizer group. So in future, one can explore the completeness of a stabilizer group and the automorphism group of a stabilizer group. Once we found the automorphism group of stabilizer group of different set ideals, one can investigate the Lie group structure on the particular stabilizer group of a set ideal. Next. So these are all my references. Next. Thank you. Any questions?
So references are very old, no?
Yes, sir.
References are...
Yes, sir. Actually, these references are very old, as well as the paper in 1999 and 2002. That time only they found some results. After that, up to till date, no one is working in that area.
So have you published this paper or submitted?
So in conference, here I submitted.
No, submitted in any journal or published?
No, sir. No, sir. Thank you.
Hi, sir. But no participants need to come. So we can. Paper ID number 38 here. Yes, sir. 38. 35 is his time is.
Hello, everyone. First of all, I would like to thank the organization committee for giving me a chance to present this work about leap functions over positive transport blocks. Next, please. Okay. Go back. Yeah, next, please. Okay, so we're going to start by a Hilbert space of finite dimension, and then we consider all bounded linear operators over this finite Hilbert space. We call this class Mn. Now, if we fix an orthonormal base, this class Mn can be identified with the class of all n by n matrices with complex interests. Okay, the motivations, or the motivation of our work is this inequality published by Odinart in 2015, which says that if you have two sequence of operators, let's say matrices, such that those operators are commute, Aj commute with Bj, then we have this norm inequality, which says that the norm of the sum of the product less than or equal the norm of the product of the sum. In this work, I'm going to present a result which leads to improvement and generalization of Odinart inequality. So this is our goal. Next, please. The outline of this talk will be first, I'll give introduction, definitions, and basic results related to matrices. Then I'll state the main result and its consequences. First of all, for any element, let's say matrix in Mn, we can define the adjoint of this element by this identity. So always for any A, there exists A star, we call it the adjoint of A, satisfies this relation, the inner product of AXY equal X A star Y. This A star is called the adjoint of A. For matrices, this A star, it's exactly the transpose conjugate of this matrix. Now, using the adjoint, we can classify our element in Mn as in different classes. For example, if A star equal A, our element A will be called Hermitian. If A star equal A inverse, this A will be called a unit element in AM. Now, for Hermitian matrices, we can talk about positive definiteness. A matrix, an operator A, we call it positive or positive definite if the inner product of AXX is positive or strictly positive. Now, for positive element or positive matrices, we can define a square root using the fundamental theorem of matrices, or what we call the spectral theorem of norm operator. Always for any element A, you can find element B. If you square it, you get A. This element usually called the square root of the matrix A. And always this element exists and unique if we want it to be positive definite. In general, for any t between 0 and 1, we can use the spectral theorem to define A to power t. Next, please. Okay, now what's a leap function? A leap function is a function, continuous, assigned to each matrix some complex number. And this function satisfies those two conditions. First, it's increasing over the positive definite matrices. Two, it satisfies this inequality. Next, please. Most of the common matrix functions satisfies this inequality. For example, trace function is a leap function. Determinant is also a leap function. The third one, or the fourth one, the product of the maximum k eigenvalues also is a leap function. Moreover, if you consider the product of the maximum k singular values, also is a leap function. And more general, if you take any unitary invariant norm, it presents a leap function. I'll focus on this last part, so I need to define what's a unitary invariant norm. So here, a norm, we call it unitary invariant if it's invariant under the multiplication by unit matrices, in the sense that the norm of ux v equal x for u and v any unitary matrices. So it's kind of this norm absorb the unitary matrices. And at the end, this norm will, if you use the singular value decomposition of matrices, this norm is just a function, symmetric function, depends on the singular value. Famous examples of such norm is first what's called the operator norm, which is S1. And we have a big class of this kind of norm, what we call Shetton P norms, given by this formula. Now, for a block of 2 by 2 matrices, usually we consider this 2 by 2 matrix where the entries are n by n matrices. Okay? According to the Schur criteria, this block is positive definite if it satisfies this inequality. This is called Schur criterion. Now, I'll define this block to be positive partial transpose if it's double positive, means the block is positive itself and the partial transpose of it is positive definite. Look at the second, we just take the transpose based on the blocks, ignoring that the blocks are matrices. Just take the transpose. We need both to be positive. In this case, we call our block positive partial transpose. According to the Schur's criterion, so we have those two inequality equivalent to saying that this block is positive partial transpose. Sometimes shortly we say just PPT, positive partial transpose. Now, it's a famous inequality for positive number, the arithmetic geometric mean inequality, which says that, just remove the screen. Okay, for positive numbers, square root of AB less than A plus B over 2, this is known as arithmetic geometric mean. The root of AB is the geometric mean, and A plus B, as you know, over 2 is the arithmetic mean. The question, can we generalize this for matrices or for operator? The answer is yes. Okay, that's fine. But we cannot define the root of A times B, because if A and B are positive, the product of A, B is not necessarily positive. So instead, we define the geometric mean of, what's wrong? We define the geometric mean of AB using this formula. Okay, it's kind of symmetric formula. Now, using this formula, the geometric mean of AB satisfies these nice properties. This product, or this geometric mean, is positive, and if A and B are commute, then we have this nice formula. The geometric mean of AB is just the root of A times B, because in this case, AB is positive. And it's commute. And then we have the famous arithmetic geometric mean for matrices. Now we're gonna extend this definition to weighted arithmetic geometric mean. Can you, next one? So this inequality, the first one, AB to power, it's called Young inequality. A to power 1 minus t, B to power t, less than or equal 1 minus ta, tb. This is called the Young inequality. So you can think of the left-hand side as geometric mean with weight 2, with weight t. And the right-hand side of it, the arithmetic mean with weight equal t. Now that we're going to have the same thing. We can extend this inequality to matrices. So we need to define what's geometric mean with weight t for two positive matrices. It's given by this formula. Basically, we can just change half by t. Next, please. Now, just simple properties of this definition. The product, the geometric mean with weight t, is positive. For t equal half, it gives us the regular geometric mean of matrices. It's not commute, but the geometric mean of A times B with weight t equal B times A with weight 1 minus t. In case A, B commute, we're going to have this similar to the weighted geometric mean of positive real numbers. And then finally, we have number 5. We have a similar formula to Young inequality for positive numbers. Okay, next please. Now this is the main result. If you start by positive partial transpose block AX, X star B, then we prove that this new block with this mean is also positive partial transpose. And moreover, we have this inequality for any leap function. Okay, the second inequality. It's true for any leap function. In particular, if we choose t to be half, we get this last inequality. This is the main result. Now, in the next slides, I'm going to take examples of L so we can get several results. Can you check the next one? Now, I'm taking L equal transpose. In the third inequality and second inequality, I'm taking L to be the norm, any norm, unitary invariant norm. Next, please. Here, I'm taking T to be the sum of the maximum of k singular values. Now, this is well known as a log majorization of of singular values. Next, please. And this is how we create. So I'm going to use the idea we have a positive partial transpose to get inequality. I need to create a positive partial transpose. Now, if you consider any two sequence of A and Bj, positive sequence in Mn, then this block is positive transpose. Now, given that, using our theorem, we can get this inequality for any leap function. Now, this is the main result. I'm going to take particular cases, and then the last one will be the norm. Take the next one, please. So here, I'm taking a special case, L equal a unitary invariant norm. Using the properties of norm, we can give more details, more improvement of ordinate inequality. Next, please. Here, I'm taking the case T equal half, same inequality. I don't know. Then, next one, please. Here, I'm taking a special case, more special case, R equal half. Now, this is the last inequality in the case L equal the unitary invariant norm. Now, this inequality present improvement and generalization of the first inequality which we started with, ordinary inequality. Thank you very much. This is the resources I used. Go to the first one.
Back. First, no, not first, second or third.
Second author.
Go.
You mean the
previous.
references?
Next, previous one. Previous slide, previous. Yes, that slide. Next, yes, see that. No, the back.
Back.
No, see that. No, you have defined, no, say, power you have considered.
You mean this one?
No. Previous slide.
Previous, go. First one.
Yes.
Yeah.
That. So see that in the last sentence, okay, a similar result can be extended to obtain 1 a to the power 1 by r.
Yes.
So where r is a positive integer, so there is no problem. And to obtain a power t, for all t belongs to 0, 1. Okay.
Yes.
So if it is valid for t belongs to 0, 1, then it is valid for other fraction also, no?
Yeah.
If we consider t equal to 3 by 2.
3 by 2? No, we consider
Then we
just...
can, is it possible, say a power 3 by 2 means a into a power half?
No, this definition works for only square matrices because we have the spectral theorem. So you can decompose.
If t is 3 by 2,
Yeah.
then we can write, no, a to the power 3 by 2 equal to a into
Yeah.
a to the power half.
Yeah, we can do that. It agrees with the regular powers. So this definition, to power t, is compatible with any power we know about matrices.
Okay.
It's compatible, so there is no problem with that. But usually A is positive matrix, so you can use the spectral theorem to write the decomposition. Then we just put any function on the diagonal. This is what spectral theorem is for, actually. Okay.
It's okay. So have any question from audience? Yes.
I can hear you now.
Sir, here for the positive definite,
Which one?
third one.
Third one? Okay.
So a Hermitian matrix is said to be positive definite, some inner product is greater than or equal to 0, you got defined right. You got defined right a greater than or equal to 0 for the notation.
Yes.
For the next point, you mentioned that a is strictly greater than 0.
Oh, you mean greater, strictly greater?
Yeah.
It works for greater than or equal. It's fine.
So I'm asking, in your notation, in the third point, whether it is greater than or equal to or strictly greater than 0.
It works for both, actually. Usually, greater than or equal, you might have 0 eigenvalues. So in this case, because all our functions are continuous, by continuity argument, we can reach to a greater than or equal. So
But
we can work with strictly greater than. You have your inequality. Because all our functions are continuous, I can go to greater than equal by limits.
That's fine, sir. But I'm asking, in that kind of matrix is not said to be positive definite, right? Maybe positive semi-definite. In your third point, you mentioned that it is positive definite Hermitian matrix.
Yes.
So for the positive definite matrix, it should not go 0 as eigenvalue, right?
It's. I don't understand what you're saying exactly. For
Just go to the previous slide.
previous slide,
Sir, in that third point, if a matrix is called positive definite,
which part? 3?
third point.
Third part. A is Hermitian.
Yes.
Positive definite if we have this inequality. Okay.
I'm asking for a positive definite matrix whether it has 0 as an eigenvalue or not.
It has positive eigenvalue or strictly positive eigenvalue.
Strictly positive, right?
If it's a strictly positive definite, we have strictly positive eigenvalue.
Okay, so for you, if it has strictly positive definite, it don't have 0 as an eigenvalue.
Yes.
Okay, so then fine, sir.
No problem. Any question? Thank you very much. You asked me, I asked you. Thank you very much.
Next, paper ID 45. அடுத்த இது பாரு. ஒரு 3 நான் ஆப்ஷன் கொடுத்துருக்கேன். இந்த பேப்பர் Is Narmada Devi here? Narmada Devi. Paper ID 182. Paper ID 281. Yes, ma'am. Are you ready? Ah. 281 கொடுத்துருங்க.
Who has been already served with the probability P2, and he can reject with the probability Q2 such that P2 plus Q2 equal to 1. And this main server, after recruitment, if there is any customer in the queue, he will start giving the service, or else he goes for an vacation with an exponential distribution. And this additional service follows phase type distribution alpha 1 T1. A normal service and optional service are provided both for the customer such that alpha 1 T1 and alpha 2 T2 following phase type distribution respectively, and optional service will be provided under the request of the customer with a probability P1. And here we have put a schematic representation of our model. Like the first, this customer enters the queue, the main server starts doing service, provide normal service. After completion, he can ask whether the customer needs any optional service. If so, an optional service will be provided, and the main server will check if the queue is less than L. If so, he'll start doing the service once again repeatedly. And if the customer in the queue exceeds L, then he'll go for opt for an additional server. This additional service will be recruited from the customer who has been already served, and this customer has to accept. He can accept or accept under the probability P2, as we have seen already. This after recruitment, the additional servers provide service for normal service as well as optional service under the needs of a customer for that L customers alone. Next. This model has been represented mathematically with the following notations like N1, N2, S of t, J1 and J2, M of t. Where N1 and N2 represents the total number of customers in type 1 and type 2 queue, and S of t represents the position of the server, and J1 and J2 represents the phase type service while providing normal and optional service respectively, and M of t represents the Markovian arrival process. And this is the status of the servers. Like when the main server is on vacation, and 0 represents the additional server is not available, and 1 represents the additional server is busy with normal service, and 2 represents the additional server is busy with optional service. The same pattern follows for 3, 4 and 5, where the main server is providing normal service, and 6, 7 and 8 represents when the main server is busy with optional service. Here we have given the state space for all those study, like omega equal to L of 0 union L of I, where L of 0 represents 0 number of customers in the system, and L of I represents I number of customers in the system for I greater than or equal to 1. And here we have given an infinite generator matrix Q, where each element represented here is a block matrix, and the diagonal elements represents no arrival and no service, while the element above the diagonal element represents the arrival process, which makes from the transition state I to I plus 1, whereas the elements below the diagonal represents a service completion, which moves from the transition state I to I minus 1. And before solving this set of equations, we have to check the stability condition so that the system, the model that we have undergone is stable. For that, an infinite generator script P has been introduced here, which satisfies a set of equation PA equal to 0 and P equal to 1. The necessary and sufficient condition for the system to attain stability is PA not E is less than PA2 plus L plus 1B times of E1. And here, this equation has been solved. For solving this model, we have introduced an infinite generator X such that XQ equal to 0 along with the normalizing condition XC equal to 1. In order to find this, after a certain period, we can see that XL plus 1 can be represented in terms of XL along with the rate matrix R power I, and this rate matrix can be calculated using the following equation, and the boundary condition has been calculated using these sets of equations. And after solving all these things, we can come to we can see the behavior of our model, and these are the few performance measures that we have been computing here. Main server, when the main server is busy with normal service, we can see that whether the additional service is busy with normal service and optional service when the additional server is not available. And similarly, when the main server is providing optional service and additional service is busy with normal service, optional service, and expected system size, and so on. And here we have introduced a cost metric into this model, so that once the model is implemented, we can see how the system is sustained even with this metric also. And here we have done a particular case so that the model has been converted into an exponential distribution for both the arrival as well as the service phase. Here no arrival matrix D0 has been considered as minus lambda, and arrival matrix D1 is considered as lambda 1, and normal service is taken T1 as mu1, T2 optional service as mu2, and all the phase type parameters has been considered as 1, and number of phases is also has been considered here 1. And for this system we have considered the stability condition, rho A equal to 0 and rho equal to 1, and here also we have checked the stability condition. These are the three sets of inputs that we have taken from the literature for both the arrival as well as service phase for exponential, error-long and hyper-exponential process. And these are the numerical results, graphical results that we have received. Like we can see that the service rate increases and the vacation rate increases, the total calls also increases. As the server delays the process, we can see that the total cost increases. And these are the few references. Thank you.
Stochastic process, no?
Yes,
so I did not find any places regarding the time dependence, no? All these events are time dependent. Arrival depends on time or service.
Rate, sir. With rate, probability rate. Yes, sir. Probability rate, sir.
So there is no time, no? Time is not required, time dependent.
No,
it may happen, no? So morning time the arrival rate is high. In afternoon time the arrival rate is low. It may be happen. So arrival rates also depends on time, no?
Arrival rate only we have considered, sir. Like arrival rate in the sense that within 5 minutes, 2 arrivals may appear, and like that. Not the whole period is considered inside the time value.
In every stochastic system, no, they are considered time or
yes.
places like
time,
that.
which is indirectly inside.
And you have mentioned was the total cost.
Yes.
Equal to, so cost depends on which thing?
On all the parameters that we have included over
Which
here.
are
like,
the parameters?
Optional service, for providing optional service and providing normal service.
Server price.
Server providing normal service and server providing optional service and all those.
No. Like cost means something you are paying some monies to
we are involving some metrics towards for each service and look over how much cost has been considered for the whole setup to be run.
That means you have a cost matrix. Cost matrix considering your server price, manpowers,
yes,
or other softwares.
Not in software, sir. Like for each applications where the server is doing, we'll be including a cost for it, just to manipulate and check whether how much cost has been involved in it. That's it.
Okay. So any question from audience? So no question?
Thank you. Thank you, sir.
Rachna, are you ready? Hello? Hello, Rachna ma'am, are you ready? No, ma'am, you are not audible, ma'am. Okay, like. Hello, ma'am. Yeah, Sheila Rani ma'am or Rachana ma'am, anyone is ready? இல்லை ரெண்டு பேரும் நம்ம கேட்கலாம், நம்மகிட்ட தான் இஷ்யூ ஏதோ அன்மியூட்டில் தான் இருக்குது பையன் கேட்கல, அன்மியூட்டில் தான் இருக்கு கேட்க முடியாது. ஆடியோ கேட்கல, ஆடியோ.
Yes, ma'am. I'm on.
ஹலோ பேசுகிறாங்களா? ஹலோ.
Yes, ma'am. I'm Sheila Rani. Can you hear my voice?
Yeah, ma'am. Sheila Rani, ma'am, you can share your screen and you can start your presentation, ma'am. You are
Yes, ma'am.
Yeah.
Ma'am, actually here I am getting notification like you cannot start your screen while the other participant is sharing, because here the Ratna is sharing her screen, I think.
Oh, okay. But your paper ID is 127, right?
Yes,
Okay.
yes, ma'am. My paper ID is
Actually,
127.
Yeah, they need to stop screen sharing.
Yes, ma'am. Now I will share my screen.
Rachana, ma'am. பண்ணிட்டாங்க. Yeah, Sheila, ma'am, now you can start.
Yes, ma'am.
Yeah.
Yes, ma'am. Now can you see my screen? Ma'am, is my screen visible?
Hello, ma'am.
Yes, ma'am. Yes, ma'am.
Yeah,
Is
you
my
can-
screen visible?
Yeah, visible, ma'am. You can start.
Yes, ma'am. Yes, thank you so much, ma'am. Good afternoon, everyone. I am Sheila Rani. I am doing research under the guidance of Dr. S. Dhanasekar. He is assistant professor in Vellore Institute of Technology, Chennai. And now my research title is Fuzzy MCDM technique for analyzing the risk factors of COVID-19 and flu. So this is my contents. First, I would like to explain what are all the contents I have in my article. So first one is abstract and introduction. Some review what I explained in this article and what are all the algorithm I created, and also my case study. So here I took case study as medical diagnosis, and also what are all the case study results I have I discussed in my discussion part, and so finally I concluded what are all the results I got. So here my abstract is, in our day-to-day life we have more problems in decision making. It's very important in our day-to-day life. So in this decision making part I have some subjects opinion, like we have more subjects, fuzzy mathematics and graph theory and business mathematics, so everything we have. But here I am choosing the subject of fuzzy mathematics. So here I am doing my work with a fuzzy multi-criteria decision making. So every case study we have to use with a real life application problem. So in this work I used a real life application problem with a medical diagnosis, COVID-19 and flu. So here we have the two diseases. These are all viral diseases. So why we need the subjects with a medical diagnosis result? So in 1965, Zade, he introduced fuzzy sets and fuzzy logic. So why he created the subject for this uncertainty and to take imprecision decisions. And so we have more types of fuzzy numbers, like a triangular fuzzy number, trapezoidal fuzzy number, Gaussian and pi-shaped and Pythagorean. Like we have more types of fuzzy numbers, but in this work I chosen triangular fuzzy number. So particular type of fuzzy number, it is depending on some application and some uncertainties. So everything we have in this fuzzy number application. So here we have more types of viral diseases also. So how we have subjects, and so this same like we have medical diagnosis problems. So in our day-to-day life we have more viral diseases. First one is influenza. So it is making some infectious diseases, especially it is making more vulnerable population situations. It is making more diseases to populational countries. And so second one, COVID-19. Already we learned about this diseases and we lived in 2019. So SARS, COVID-19, and so everything is joined with the name COVID-19. So it is making a global pandemic, and so the symptoms of COVID-19 and flu both are same in some situations. And so HIV it's also another virus diseases, and so it is not a common virus for every disease. So it's a particular virus, and it is making some disease to some persons, so who are all make some problems in their human disease and human bodies. So hepatitis virus, it is making and it is giving inflammation to the liver, and so it is making dangerous part to the liver, and it is damaging every part of liver in some overtime. So Ebola virus, it is also a common virus in some countries, but it's not in India. It's in some places in India, but all over the countries, the Ebola viruses is making most of the problems like fever, severe headache, and muscle pain, body pain, and bleeding problems. Everything the patients are getting from Ebola virus. And so here, this is my literature review. So in this, can you hear my voice, ma'am? Hello. Yes, ma'am. So am I audible? Am I continue this one?
Yeah, you're audible only, ma'am. You continue.
Yes, ma'am. Thank you. So here, this is my literature review. So 2016 onwards, I took this work. What are they doing? So first workers, Zhang et al. In 2016, he did research. So they did research on inpatient admission. So who are all living in hospitals. So how they work, how they were living by disease. So he used the Vicar technique. And 2020, Mohammed et al. They did a diagnostic model by benchmarking methodology for COVID-19 disease. And in 2021, Naeem et al. They did research and they created an algorithm by using TOPSIS and Vicar via Pythagorean fuzzy set. So here I am choosing TOPSIS and Vicar technique for same. So here I chosen the parts for triangular fuzzy number. So here also I am using medical diagnosis field, but here I chosen disease for hepatitis A and hepatitis E. So next we are moving for why we need a fuzzy MCDM technique for medical diagnosis. So here why we need fuzzy MCDM technique. So first one, we have some uncertainty. For example, if a patient has some uncertainty in he has fever 92 degrees Celsius, but morning time he has different degree, afternoon time he has different degree, and night time he has different degree. So we are facing some uncertainty in this place. So here we need a fuzzy MCDM technique to handling uncertainty. And second one, we need to create a subjectivity. So what is the subjectivity here? We have more preferences to, for example, if a patient has a cold and a fever and everything he has. So which subject is more important? So for that we need to take a fuzzy MCDM ranking. And third one, ambiguity. Ambiguity is also an important. So when we have more complexity, at that complexity we can understand modeling ambiguity is also important. So for these three reasons, I chosen fuzzy MCDM technique for handling medical diagnosis problem. So this is basic definition for fuzzy set. So in 1965, Lord V. Zade introduced fuzzy set. So here we have an element and a membership of an element. That is the definition for fuzzy set. So here we have universal set A. So here from the universal set A we are taking fuzzy set X bar. So through this X tilde we are taking an element A and membership of element A. So it is defined by Lord V. Zade in 1965. And after that a fuzzy number. So when we have fuzzy set, so we can define fuzzy number. It is defined from real number to 0, 1. So here when the three conditions are satisfying from fuzzy set, we can say the number is fuzzy number. And so here I chosen triangular fuzzy number. So we have I have a diagram for this triangular membership number. So here we have A, B, and C. So A is minimum, C is maximum, B is the indeterminate value in between A and C. So we can take A, B, and C. So here I am substituting A is 0.1, B is 0.2, C is 0.3. So here I am taking these values and we can substitute in this one. So I can calculate the membership function. So this is diagram. So this is an explanation why we are choosing the diagram for this definition. And next we are moving for arithmetic operations. So every number has some different arithmetic operations. So triangular fuzzy number is also having arithmetic operations. So we are having addition, subtraction, multiplication, division, like basic arithmetic operations here we are having. So this is my hybrid technique. I chosen two techniques like TOPSIS and Vicar. So how I defined this article. So first one, I took the alternatives and criteria. And second one, I created a linguistic relation matrix. And third one, we changed the linguistic matrix to fuzzy triangular matrix. And fourth one, we did a defuzzification. And fifth one, we have to take a normalization and a weighted decision matrix. And now and after these 5 steps, we can use our TOPSIS and Vicar. So TOPSIS, we have 3 parts. First one is ideal best and ideal worst. Second one is positive ideal and negative ideal, and relative closeness to ideal solution. This is for TOPSIS. So the full form of TOPSIS is technique for order preference by similarity to ideal solution. And so Vicar. Next we have Vicar technique. This is a Serbian word. So for this Serbian word meaning is we have compromise solution by using this technique. So in this technique we can take the values for S, R and Q. So we can take compromise solution by using this technique, and when we have rankings in between TOPSIS and Vicar, we can compare and we can analyze which one is the best by using this hybrid technique. So this is my algorithm. So this is the shortest diagram of algorithm. So here I am explaining everything. So first one, I defined alternatives and criteria. So I gave name to every alternative and every criteria, like alternatives are R1, R2, RM. So till M I have. So next we have criteria. So criteria we are taking like C1, C2, etc. CN. So decision makers. So here decision makers for medical diagnosis are doctors. So D1, D2, etc. till DK we have doctors. And B created construct of decision matrix. So how we need to construct a decision matrix? So here I have I thetum and J thetum. So I are alternatives and J are criteria. And aggregated triangular fuzzy matrix. So here we don't have only one doctor. Here we have 3 doctors. So here we need to aggregate 3 doctors data with a triangular fuzzy matrix. And next we have to calculate the weighted values from every weighted values of a normal situation and a critical situation, like in our day-to-day life or real life application problem. We can construct weighted values for every criteria, and here one important thing is when we sum every weighted value we can get a 1. So next we have to normalize the weighted matrix. So when we are normalizing this one, so we have more formula for normalization. So here I am choosing one formula for normalization is Nij, which is equals to Rij divided by.
Sheila Rani ma'am, you are having
Yes,
two more minutes. Please make it fast, ma'am.
Yes, ma'am. Yes, ma'am. Sorry. Yes, ma'am. Now I'll make first. Yes, sorry. So here we have a weighted normalized matrix. We have to multiple, and so determine B plus and B minus. We have to get ideal solution for TOPSIS, and Ricard technique we have separate. So for this TOPSIS we have separation measure. After this one we can move for Vicar. So for this TOPSIS we have relative closeness, and for Vicar we have maximum and minimum value. So this is my algorithm. So we can substitute every value we are getting for we are getting the data from doctors. So this one is for COVID-19 image. So why I chosen only COVID-19 and flu means here we can understand the similarity for COVID-19 image and flu image. So COVID-19 and flu we have same similarity structure, and also it is making some common situations and common symptoms to every patient. So I chosen these 2 diseases. So here I have more alternatives. So when a patient have a fever, cough and tiredness, loss of taste or smell, so throat, headache, aches and pain and diarrhea. So we have more risk factors, but World Health Organization they reported 12 risk factors are more dangerous, and they don't know which symptom is common for COVID and which symptom is common for flu. So here we have to take the risk factors for both disease COVID and flu. So here we took notation to R1 to R12. So here criteria when the patient having normal situation, that like normal is C1, and second one is borderline, and third one is early COVID and flu situation, and final one is COVID later COVID and flu situation. So here we have linguistic terms. For example, doctors they don't know the fuzzy triangular numbers, just they know what is the linguistic term. They can say like the fever level is very low, the cold level is low, medium, high. So they can say the linguistic terms, and we can use fuzzy triangular numbers to calculate which one is best and which one is low. And next we have to move for what are all the decision makers opinion about COVID-19 and flu. So this is first decision maker, like first doctor's opinion. So they are saying like first R1 and first C1, it is comparing when they joined R1 and C1 the situation is very high. So they gave the data for first decision maker opinion, and second decision maker opinion we have, and third decision maker opinion. So like we got 3 decision makers opinion for this problem. And so weighted values also they gave parts for weighted value, like first decision maker they gave first criteria is very high, and so second criteria is high, like they gave a weighted value for every criteria level. And after that we have to substitute every value for aggregated triangular matrix. So when we have 3 decision makers opinion, we have to collect every values and we have to aggregate the triangular fuzzy number, and after that we have to defuzify by using CFCS algorithm. And so we have already we used normalization formulae like Rij divided by square root formula. Like we can substitute normalization and we can choose which one is best and which one is worst from this risk factors alternative. So for example in C1 the best is very highest value, the worst is very lowest value. So here 0.146 is highest and 0.0986 is lowest. So here we are getting best value and worst value, and we need to get the TOPSIS ranking. So here in this one R10 is TOPSIS ranking. So R10 is the first alternative. And so here next we are using Vicar alternative. So for this Vicar problem, we are choosing P star and R star P minus R minus. So we are selecting from the same previous topsys table. And so we are having QI value from the descending order. And so by using this one, we are taking the rankings. So here also we can understand R10 got first rank. So here, by using topsys and Vicar technique, we can understand R10 got first rank. So when a patient is having the risk factor R10, he or she should go to the hospital and they should be in ICU. So here R10 is, so what is the R10 here? So we need to understand R10 is shortness of breathing. That is R10. So this is comparison in between rankings for topsys and Vicar. So here in this work, what I did, so here in this work, I chosen topsys and Vicar technique. So I designed an hybrid technique by using topsys and Vicar. So we analyzed everything for COVID and flu. So what are all the risk factors are they discussed in World Health Organization? And so by this risk factor R10, it got first rank, and we know this is the first one in World Health Organization, and most of the doctors they recommended R10 is first one. So we proved R10 is got first place by using this shortest algorithm. So R2 it's the last rank. So R2 is when he has body pain. So at the time there is no need to go to ICU part, because doctors are confusing while which patient they need to more help to help in ICU. So what are all the advantages we got in this work? So here we improved robustness. So robustness means here just we used two algorithms and we make a hybrid algorithm. So decision making process is very easy when comparing with other algorithms. So balancing sensitivity and stability. So here the stability value it didn't change by anything. So the sensitivity analysis it's also giving the correct rank. For example, we can use any other outline process for this one. We can compare our results with another result. So the ranking is also similar with 90% and 95%. So here next we can handle under uncertain information. For example, just doctor said it's very low, very high, that's only. But we can use triangular fuzzy number and we can analyze and we can get rank from fuzzy MCDM. So by uncertain information, we can calculate correct rankings and consideration of multiple aspects.
Your time is over, ma'am. You can conclude it. You could come to the conclusion, ma'am.
Yes, ma'am. Sorry.
Yeah.
Okay. So here, so the conclusion, the comparative study we did. Yes, that's only. So I would like to acknowledge the Dr. Tyagarajan and his team. He helped a lot and he gave us a best results. And so he suggested more techniques. And so he suggested the data sets. So what are all the data sets we can use our research? So these are all our references. So thank you so much, ma'am. Thank you so much, everyone.
Yeah. We'll wait for the questions, ma'am.
Yes, ma'am.
Thank you for your presentation. So go to the slide, your decision matrix. You have prepared no decision matrix. Go to that slide.
Ma'am.
Sir, are you? Yes, ma'am. Can you hear my voice?
Decision matrix. Go to the decision matrix.
Ma'am, I could not hear sir's voice clearly. So, can you tell me? So, what is sir is asking with us?
Ma'am, just go to your decision matrix slide. Sir is asking.
Yes, ma'am.
Yeah.
This decision matrix, first decision matrix, ma'am. First decision maker opinion and second decision maker opinion.
No, this is not the decision matrix. That one written in terms of small r, R11, R12 like that. Okay, go to that slide.
Sir need decision matrix slide, ma'am. This is the table, but sir is asking decision matrix slide.
Yes, ma'am. So this is aggregated triangular fuzzy
No,
matrix.
next to one, I think.
Oh, go.
Next one, or previous
Yes, ma'am.
one.
Defuzzified matrix.
Is this the one, sir?
No, go to the theoretical part.
No.
This is your case study, no? Go to the theoretical part.
Previous slide. Theoretical part, sir is asking.
Okay, ma'am. Okay, so theoretical part. This one, ma'am.
Okay.
Yeah,
wait here,
yeah, this one, ma'am.
Yes,
So
ma'am.
what is the
Step 4.
previous slide?
Yes, ma'am.
Yeah.
Yes.
Yeah.
So what is the value of R? R1, 1, 1, 2, 1, 3? It is lies between 0, 1 or any other values?
Ma'am, can you hear the question, ma'am?
No, ma'am, I could not hear.
Yeah, sir is asking what is the value of R11, R12, and is it lies between
seed data set, and dB index value indicates that this provides better clustering method. Okay. So these are some references which have been used.
So thank you, Professor Som.
So thank you very much.
And
if there are some
so
questions,
is there any
please.
question from the participants?
Well, I think
From the
I
house?
am on time because of some problem. It was little delayed. Hello.
Hello.
Any question, please?
So any question from the participants? So no questions. So I am having one question. Why are you interested to use that quad tree? Hello? Oh, it is not. Sir, why are you interested to use that quad tree? Hello?
Yeah. Are you getting me? Okay. Is there any question? I have finished. Yeah.
Hello?
Okay.
Are you getting my voice?
Yes.
So,
Please.
why are you interested to use that quad tree?
Can you speak little less loud?
No, if you see, you can use that decision tree also or other any technique.
I'm not getting properly. Can you message or? Yeah. Decision tree. I have not compared with decision tree, but I have compared with k-means. Okay. But with k-means it is quite better. Quite better. That can be used certainly. And maybe this may be comparable also. Yes. I'm getting quite better result. Quite better. Of course, this IRIS data set is a very well-known data set. And another seed data set that is also a well-known data set. And I hope that with other data sets. It is not the point. We are getting cluster centers and then, okay, and from cluster centers, where is the data located? Okay, nearby data set, that is neighborhood data set. Okay, this is a new problem you are asking me. Anyway, we'll try how to do that one. Okay, certainly we have pixel, we have to generate from English language to some other, okay, relevant data and then analyze. Maybe in this case it may fail. I do not know. I cannot say anything about, okay, unless we do. Okay. You may have some other distance also, but hope you will get the same result, more or less same result. Yeah. But Euclidean distance technique is quite very much in use and very standard technique. That is why I have used Euclidean distance. Of course, a little bit but it is going to give you a better result. That is more important. That is. Yeah. Yes. Yes. Maybe little bit, but if it is taking less time, that is more important for large purpose use. Okay. Yeah. Okay. Thank you for nice hearings. Sorry, I could not attend your event inaugural because I had classes. Uh, yeah, I know, but last month I visited some other place. Yeah, certainly, maybe next time where you are going to arrange, I will be able to go. Mm. Okay, okay. Thank you, Dr. Giri and Dr. Venkatraman. Yeah, Professor Venkatraman. Yeah. So let me close the slide slow. Yeah. Is there anything? No, is there anything? No. Okay, okay. What is the next lecture? Who is going to give? Maybe in the same link or some other link? Okay, okay.
So I now request Dr. Professor R.K. Sharma to give a brief introduction about Madhumangal Pal for his invited talk.
Well, friends, a very good afternoon. So it's my great honor and pleasure to introduce to you as the last speaker of the event, Professor Madhumangal Pal. He is a professor in the Department of Applied Mathematics at the Vidyasagar University, Medinipur, West Bengal. And he has been a friend for a long time, right from IIT Kharagpur. And of course, for a mathematician, the best introduction is by his work. And he has been doing very good work. And I won't like to take more of your time for introduction itself because he has to deliver a talk. And therefore, without wasting much time, I would like to invite Professor Pal. So it's a pleasure and honor. Please welcome Professor Madhumangal Pal from Vidyasagar University for his distinguished talk. Please, sir.
Thank you, Professor Sharma. And good afternoon. And I think all the participants are tired physically as well as mentally. So first of all, I am very grateful to the organizer for inviting me to deliver a lecture in this mega event, particularly Professor Yagner and Professor Devashish Giri. Put here. So, I'll discuss regarding topological index of graphs and its applications. So, you know, the graph theory is a very important subject of mathematics. Basically, mathematicians are working on graph theory in algebraic sense. And also the computer scientists, they are also working on graph theory in algorithmic sense. And also the graph theory we use in many different areas of science and technology, even in social sciences, also in medical sciences, due to its application. So now I will discuss an application of graph theory in chemistry. So that particular type of graph is known as your chemical graphs. That means the graphs coming from chemistry, particularly the your carbon compounds. So from carbon compound we can construct a graph, and from that graph we can analyze some physiochemical properties of that type of molecules like that. So this is an example of graph. So graph basically we can represent in two forms in terms of two sets. One is called the set of vertices denoted by V and set of edges denoted by E. So this is the algebraic or mathematical representation. And another representation is in terms of your pictorial representation. So this is the pictorial representation. In pictorial representations, in this diagram, see that there are two types of object. One is small circles or dots, and another is some straight line or arcs. So dots are nothing but your vertices, and arcs, that means straight line or curved line or circular line, that's nothing but the edges. Okay, so this is the very simple overview of a graph. Now in chemical graph theory, or the molecular structure of compound is often represented by a graph. In chemistry, that means chemical graph theory, saying that the chemical graph theory or molecular graph theory, that one coming from the molecules of a chemical compound, particularly I am saying carbon compound. See that to understand these topics, we need a basic idea on carbon chemistry. So we are familiar with atoms. No, atom means hydrogen, oxygen, carbons. These are called the atoms. And collection of atoms forms a molecule. See that the lower part of this picture is a molecule. Which molecule? Oxygen molecule. Sorry, water molecule. H2O. H2O is here. So this is your molecule, water molecule, and its contains 3 atoms, 2 hydrogen and 1 oxygen. You know the bond of oxygen atom is 2, or valence of oxygen atom
is 2 and valence of hydrogen atom is 1. So there is one edge from each hydrogen atom and 2 edges from oxygen atom. Why it is not pointing here? Okay. So we are familiar with this type of diagram, no? In class 11 or class 12 in chemistry, we saw this type of diagram. See that here, C10H12, H22, C10H22, this is a particular your compound, this is coming from your alkanes group. Alkanes group is there. So C10H22, general formula is CnH2n plus 2. So that one is known as alkane or paraffin groups. So when we choose n equal to 10, then we have this type of compound C10H22, and this is the left side figure is our conventional diagrammatic representation. We saw this type of diagram in our chemistry book in class 11 or 12 like that. And right hand side figure, see that in the right side figure we have removed all the hydrogen atoms. From the left hand side diagram we remove all the hydrogen atoms. After removing the hydrogen atom, we obtain this right hand side figure, and this is a graph. As by definition of graph, the right hand side is a graph. Particularly this is a tree. Tree is a special type of graph, so right hand figure is a tree. Okay. So usually we remove the vertices corresponding to hydrogen, and the resultant graph is known as, see that the molecular graph, this is also referred as chemical graph, or this is also referred as constitutional graph. Okay. So see that the molecular graph of acyclic compounds are trees. Trees means there is no cycle in the graphs. For example, alkanes. Alkanes is also known as paraffins. So its general formula is CnHm. Okay, that means C number of carbon atoms are there and M number of hydrogen atoms are there. So this kind of your compounds, from this type of compounds we can construct graph. So see that in this type of compound there is no circuit and no multiple bonds. No, in carbon chemistry we know single bond, double bond, this type of bonds are there. But this paraffin or alkanes group, there is no circuit and no multiple bonds. So that means the reduced graph is a tree. And number of vertices is n plus m. Why n plus m? Because in this type of your graphical representation, there are n number of carbon atoms and m number of hydrogen atoms. For each atom, we have a vertex. So total number of vertices is n plus m. And n vertex with degree 4. Carbon, you know the carbon atoms has valence or your degree is 4. So n vertices with degree 4 and m number of vertices with degree 1 means hydrogen atom has a valence 1. So the total number of edges is 4 into n plus m into 1. So 4n plus m by 2 because one edge is counted twice. So total number of edges of this type of graph is 4n plus m by 2. Okay. So this formula CnHm represent alkane if and only if m equal to twice n plus 2. This is the particular case of your alkanes or paraffin groups. Okay. So lower figure see that there are first 3 alkanes. First 3 alkane means when n equal to 1, 2 and 3. When n equal to 1, then it is CH4. So CH4 represents methane, no well known your chemical compound methane. When n equal to 2, it is ethane, C2H6. And when n equal to 3, it is propane. So these are the first 3 your alkanes or your paraffins like that. If n equal to 4, then it has 2 isomers. Isomer means same your number of vertices and same number of edges, but their connectivity are different. So there are 2 different isomers. So if n will increase, then number of isomer will increase. So this is the very important and complicated things. So there is a big question, for a given n, how many isomers are there? So using the graph theoretical concept, that number of different isomers are evaluated long time back. So this was the basic or fundamental problem of chemistry. So see that the leftmost figure is a microscopic representation. So this is a chemical compound. Microscopic picture is this one, and second picture is a three-dimensional picture you're drawn by the chemist, and the third picture is drawn by two-dimensional picture drawn by a mathematician, graph theoretician, and the last picture is drawn by a graph theoretician removing all hydrogen atoms. Okay, so this is the corresponding conversion from your chemical compound to a graph basically. So there is a software to generate that kind of your diagrams. So a lot of softwares are there. I am not discussing about it. So my objective of the talk is topological index or topological indices of graphs, particularly the chemical graphs. So the question is, what is topological index? So from that word topology, we are generally think about a topology. No, we are studying in pure mathematics. So it has one set of objects and there is a distance. So there is a graph topology. There is no question about the graph topology, but here topology means the structure of the graph. Not your distance is not defined. Set of vertices and set of edges are there, but distance is not defined, but we are considering the structure of that particular type of graph. So for this reason we are called topology, topological graph index. Also it is known as molecular descriptor. That value, the topological index, represents some your physiochemical properties of some molecule. So it is called molecular descriptor. So as a mathematical formula, topological index is very simple mathematical formula, can be applied to any graph. Any graph, it may be a molecular graphs or any arbitrary graphs, but it has some properties or it has no properties like that, depends on the formula used to find the topological index. So lot of different topological indices already defined. The first one is Wiener index, then Hosoi index, hyperwiener index, extruder index, Randing index, Zebra's index. Lot of indices are defined. Even then, nowadays, you can define, anybody can define a new type of topological indices. So there is a big chances or big scope to work on topological graph theory or chemical graph theory. Okay. So Wiener index, I am just defining Wiener index. What is Wiener index? This is a very oldest, that is the first topological index defined in 1947. Hello. Antivirus protection. So this is the oldest, simplest your topological index, Wiener index, and defined 1947. So originally it was referred as path number, not topological index. Wiener referred as path number, but after that the people define or referred this as a topological index. So what is the definition? For a given graph, the Wiener index is denoted by say W of G equal to half of sum of the distance between the vertices U and V. So distance between the vertices means all paired distance, distance between any two vertices. So sum of the distance between any two vertices, and that one is divided by half, because when we are considering the pair of vertices, same edge will come twice. So for this reason, the entire expression is divided by 2. Now what is the definition of distance? Distance between two vertices means number of edges between the vertices. Okay, so this is the weights. So Wiener index is called distance based topological index and defined in 1946. Undirected graph, because the chemical graphs are all undirected. Okay, that's why all these definition are valid for undirected graph. now you can define for directed graph, there is no problem, because each undirected edge can be replaced by two directed edges. Okay. So, no, not for that reason, because every edge is considered twice. So, for this reason it is divided by 2. Okay. Not for undirected graph or directed graph, because every edge is considered twice. For this reason it is divided by 2. And it is developed, see that what is the importance of this your index. So, it is written in red color, it is developed to determine boiling point of paraffins or alkanes. This is the very, very important things. Okay, so what is the important I am saying again? So, we are to determine the boiling points of water. So, what is the process? We are heating the water and measuring the temperature when the water starts the boiling. No. So, the Wiener index, see that the Wiener index is different. Without your chemical, exact chemical, without your exact experiment, from this mathematical formula and its chemical formula, we can determine the boiling point. Without need of water, without heating, without any practical things, we can determine by considering the chemical structure or chemical formula, we can determine the boiling point. So, this is the very, very important your theory, we can say the mathematical theory, reduce the actual experiments. So, the Wiener index developed to determine the boiling point of paraffins. I am saying or showing the slide how it is possible. And this paper published in Journal of American Chemical Society, that was very famous journal and published in 1947. And see that in the left hand side the graph containing your 6 vertices and right hand matrix. That matrix is a all pair shortest distance. Okay. Right hand matrix basically a distance matrix between any two vertices, and sum of the elements of the matrix is 46. Sum of all elements of the matrix is 46, but the lower part or upper part represents the all pair shortest distance or all pair distance. Distance means always shortest distance. So, it is divided by 22. So, the Wiener index for this graph is 23. Okay. So, this is the mathematical value and there is no connection with the boiling point of this type of structure. Now, see that the Wiener index, using the Wiener index and the polarity, in the first sentence see that the W be the Wiener index of a chemical compound, P be the polarity number. This is also the terms coming from chemistry. Polarity number means number of carbon atom pairs separated by 3 bonds. That means distance 3. Number of carbon pairs separated by 3 bonds or 3 edges. So, that number is called the polarity number. So, P is the polarity number. It is coming from the structural representation of the chemical compound, and W is determined by that formula. So, W and P depends on the given chemical compounds. Okay. So, equation 1 represents BP. BP means the boiling point of a particular chemical compound equal to A, B, C. That means AW, B into P plus C. A, B, C are the constant. Okay. The parameters we can say these are the parameters. So, based on the previous actual experimental data of all paraffins, starting from N equal to 1, 2, 3, not 1, 2, 3, 4, 5, 6 up to certain paraffins, means we are collecting the actual value, actual boiling point of say first 100 alkanes. We have experimental data for first 100 alkanes. We are fitted this equation. This is a regression line basically. So, based on the first say 100 data or say 50 data, we can determine the value of ABC. Okay, like your curve fitting, straight line fitting or regression line fit. We can determine the values of the parameter ABC as this one equal to say 0.6863 like that, plus minus something errors. Statistical error also determine. B equal to 4.766 equal to 24.96. So, these are the values calculated from your based on some your some initial values of n equal to 3, 4, 5, 6 like that. So, see that here this formula is valid for not valid for methane, ethane and propane because their polarity value is 0. So, except these 3 your alkanes, this expression in ABC based on some first 50 alkanes. So this is the your connection or application of your topological index to find the chemical property of your any kind of chemical compound. So this is the important things of your Wiener index or topological index. So the points, this dot basically in this diagram, the dot represents the experimental data. Okay, experimental data, and from this experimental data, and this experimental data is coming is plotted for first 147 alkanes. That one mentioned in the caption. So boiling points of lowest 147 alkanes calculated from the your actual experimental data, and that one is plotted, and based on this value we have calculated the value of ABC, and also we have calculated, see that the capital R represents the correlation coefficient. You know the correlation coefficient lies between -1 and 1. If it is close to 1, that means we can say the data are highly correlated. And if it is close to 0, then we can say the data are not correlated. Okay. So this value, see that the correlation coefficient equal to 0.975, means very close to 1. So we can see that your experimental data and this regression line gives the almost all exact value. And S is the standard deviation, is equal to 8.06 is the standard deviation. Okay. And see that that formula, equation number 1, is slightly modified by some other researcher. This equation actually given by, or these studies are made by Wiener, okay, in his paper. But this one is modified by some other researcher. That equation 1 is modified by, see that the BP equal to AWR. In the equation 1, it, and here WR means W by N square. W means the Wiener index, N means number of your number of carbon atoms. Here mentioned here, N is the number of carbon atoms. So this term is slightly modified. Okay, or we can say that the Wiener index, this term is scaled by 1 by N square. Okay, so for this equation and for the same data set, the value of A, B, C are calculated as in this one, and see that in this case the R, correlation coefficient, becomes 0.995. It is more close to 1. Earlier it was 0.975 and now it is more close to 1. It is your 0.995, and standard deviation 3.74 reduced. More standard deviation more means the data are more scattered. Standard deviation is less means data are more closed. So in this case, the standard deviation was 8.06, and the modified expression, for the modified expression, standard deviation is reduced to 3.74. Okay. So this equation more my appropriate equation to find the boiling points of the alkane. So see that this is the straight line is the regression line, and the other dots are the your actual experimental data taken from 147 alkanes. Okay. So this is the modification. Now there are a lot of your upper bound, lower bound for different type of graphs. So see that here we have drawn two graphs. So say left hand side is a complete graph. Complete graph means the graph whose every vertex is connected with or adjacent with all other vertices. Now that graph is known as your complete graph. So left hand side is a complete graph containing 5 vertices, and right hand side is also complete graph, but it has more vertices. So more edges are there, so it looks is very nice look basically. So for this graph, for this graph means complete graph, the Wiener index is minimum. That means we can say the Wiener index is minimum for complete graphs. So if the graph contains n number of vertices, so the Wiener index of this graph is NC2. NC2. So this is the lower bound of Wiener index, and if the graph is a path, then Wiener index is maximum, and its value is 1 by 6 into n square minus 1. So this is the upper bound for any graph. So for any graph, the Wiener index lies between NC2 and 1 by 6 into n square minus 1. Not necessary molecular graph. This is true for any graph. This is any, because see that in the carbon chemistry, no, in carbon chemistry we cannot for any kind of carbon compound, there is no graph look like your this one, complete graph. The carbon, the alkane, paraffins we have discussed. Now for paraffins and alkanes, the graph should be a tree, or it may be a path. Okay. So this result is valid for any arbitrary graph. Yes. Because see that now for complete graph, the distance between any two vertices is only one. Only one. So this is the minimum distance. And winner index is based on your distance. So distance is minimum for complete graph. So obvious it is minimum. And for path, the distance is maximum. See that for the first vertex to last vertex, vertex 1 to 5, distance is 4. And this is the maximum, no. If it is cycle, then the distance will be 3. Maximum distance will be 3. Containing 5 vertex. So this is true for any graph. And after your development of winner index in 1975, after a long time, after say 28 years, in between them, there is no significant work have been published on winner index, okay, or topological index. So after 1947, in 1975, Randix defined another topological index based on the degree of the vertex. The winner index is based on distance between the vertices, but Randix index is based on the degree of vertices. Degree of vertices means, what is the degree of a vertex? Degree of vertex means number of adjacent edges, no, associated to a particular vertex. So that one is called the degree of the vertex. So based on degree of vertex, Randix define this kind of your topological index. So summation over every edge, UV belongs to E, means this is valid for every edge. So du and dv. That means for an edge UV, there are two end vertices U and V. So their degree and product and to the power minus half. So this is the Randix index. Okay. And Randix generalized his index by introducing or replacing minus half by alpha. So this is called the generalized Randix index. For different value of alpha, see, very important thing is for different values of alpha, we have different topological index. If you consider minus half, then this is exactly equal to Randix index. If you consider alpha equal to 1, then there is another index. If you consider 2, another index. If you consider 3, another index. That means for different values of alpha, we have different topological index. Okay, so by putting different values of alpha, you can define different type of topological index. But that particular your topological index will be important if it has some mathematical result, interesting result, or if it has some application, real life application. It may be in chemistry or it may be in some social to solving the social problem or any other mathematical problem. So there is a lot of scope to work on this your study, okay, or on this topological index. So good correlation ability for many physical and biochem properties are available or explained by Randix index. So for the same graph, see that the leftmost figure is a just three-dimensional figure of any 2-methylbutane, and middle one is your the chemical diagram, and formula is C5H12, and rightmost figure is the hydrogen suppressed diagram. Hydrogen suppressed diagram or chemical graph we can say, and this is basically a tree. No, there is no any circuit, so it is called the tree. So for this tree, that means for the rightmost diagram, the winner index is 18. We have calculated as the definition of winner index, it is 18. But for for the same graph, the Randix index is calculated as per definition of Randix index, and it is 2.270. Okay, so for different formula, it is obvious different value will be there. No, for the same graph, different topological index, different value will be available. Now for isopropane, basically see that for these graphs, some places there are double bonds. Okay, double bonds are there. So right hand side hydrogen suppressed graph is the right figure. So right figure is not a tree because some pair of vertices, there are parallel edges. Double bond means parallel edge between the vertices. So winner index is only valid for tree, not valid for any other type of graphs. So this graph is not a tree. So for this graph, we cannot calculate the your winner index. Okay, that one written here. But the Randix index is equal to your 2.270. So see that the winner index has some limitations. No, but Randix index can calculate the value of some more graphs. Okay. So this is a cycle with your cyclohexane. So this is the your name coming from the chemistry. So different compounds have different names. So C6H12, and the hydrogen suppressed graph is the cycle. Very simple cycle containing 6 vertices. And this is also not a tree. So for this graph, we cannot calculate the winner index. But for this graph, the Randix index is 3. As per definition, it is equal to 3. Okay. Now recently, this is not recent definition, but this is another definition, and it is called the inverse index. Okay, inverse degree index. Because see that the du, here notation I have changed. In previous slide we have mentioned degree means d within bracket u, but here just suffix we have used. Both are degree, represents the degree of the vertex u. See that this is summation u belongs to v of 1 by degree of the vertex u. Okay, so this is the inverse degree, so it is called the inverse degree index. So this is a new type of your topological index. And see that it is very interesting thing is that the first expression, first summation is over all vertices of the graph. And in the second expression, see that the second expression is summation is taken over all edges. It is first one is all vertices, and second one is for all edges. And the formula is changes to 1 by du square plus 1 by dv square. Both expression gives the same value. So this is called the inverse degree. So a very interesting result has been published in one paper. I forget to cite this paper here. That paper published in 2023, this year. Few months back, that paper is published. And in that paper, there are lot of applications. They have shown using your inverse topological index. They have shown lot of interesting topological properties, chemical properties using inverse topological index. So, and see that the general first one, equation number 4 and 5, these are the general first and second Zagreb index. Zagreb index is another very important your topological index. So equation 4, see that the definition m1 power alpha g. This is the first general Zagreb index equal to summation over all vertices du to the power alpha, okay, degree power alpha. And in second one, see that in second one, m2 alpha, suffix is 2, power is alpha of g, equal to summation taken over all edges of du dv power alpha, okay. So the summation taken on all edges, second one, and first one, summation taken on vertices. So these are the basic differences. And for different values of alpha, we have different interesting graph properties. So see that if alpha is taken as 0, the m1 0 represents the number of vertices. So very interesting thing for alpha equal to 0, it represents the number of vertices. If alpha equal to 1, then from first expression we have twice m. Twice m means m is number of edges, so twice m means double of number of edges. So that is coming from that expression. And when alpha equal to 2, that represents the first Zagreb index. That one denoted by m1, Zagreb index. And if alpha equal to -1, then it is nothing but your inverse index. Okay, inverse topological index. And if it is 3, then it is another topological index called the forgotten index, and that one is generally denoted by F. So see that for a single formula generates different type of topological index. So that's why it is called the general first Zagreb index. And for the second case, for the second formula, equation number 5, for different values of alpha, we have different results. See that when alpha equal to 0, it represents total number of edges in the graph M. If it is minus of, it is the Randex index. Already I have mentioned. And if alpha equal to 1, then M21 represents the second J-graph index, the standard second J-graph index. And when alpha equal to minus 1, it is modified J-graph index, and many more. Okay, so for different alphas, we have different your topological index. And 2-3 years back, I forget exact year, this one author is known to me, very well known to me. He defined another type of topological index based on degree of neighborhood degree. Okay, so first one, winner index based on distance, second index and J-graph index based on the degree of vertices, and this one, ND1, ND2, ND3, all these things are defined based on the neighborhood degree. Okay, neighborhood degree, that means the sum of the vertices of the neighborhood, your neighbor vertices. So using this concept, see that ND1 equal to summation over all edges root over delta G of u into delta G of v. So delta G u means the degree of the vertices of all the neighbors of the neighbors of u. Similarly for v and other things. So second one, you see that the second ND2 equal to delta G u plus delta G v to the power minus. All these terms, all these definitions are similar to our previous existing definition, but previous definition uses either distance or degree. Most of the topological index are based on degree, but these people, the definition are modified based on your neighborhood degree. Similarly, ND3 has defined ND4. See that ND4 and ND2. In ND2, see that the sum of the degrees to the power minus half. And in ND4, see that the product of the degrees to the power minus half. So sum gives one type of result and product gives another type of results. So similarly, ND5 and ND6, lot of parameters he has defined. And he also presented some interesting results. So see that the first one is n means 1, it will be 1. N1G equal to sum of square of the neighborhood degree. Okay, second one is the product of the neighborhood degree. So similar to these are the similar to the your first and second J-graph indices. And see that the first theorem is important. ND1, the first index is bounded by m into M2 to M2 star G. M2 star G means second J-graph index. Okay. So the upper bound of ND1 equal to root over of this expression. So ND1 is less than your second J-graph index into number of edges of square root of this expression. So he has proved there is a upper bound in terms of your second J-graph index. And he also proved that the equality will be hold if and only, this is if and only if result, if the graph is regular. Regular means all the vertices have same degree. All the vertices have same degree, then the graph is called the regular or complete bipartite graph. So for these two cases only, the equality will be hold. Otherwise, the expression will be strictly less than. And similarly for other result, ND1 of G is less than equal to this expression. So similarly, he has proved several your upper bounds, lower bound, etc. These are the another example, another bounds. And the application, he has given very nice application of ND1, ND2 up to ND6, your topological indices. So we have considered here some physiochemical properties of chemical compounds. Okay. So first one, see the eccentric factor. The mathematician, the computer scientist, we have forget all these terms. No, eccentric factor, one chemical property. Then entropy, little bit we have remember, no, entropy of chemical compound, enthalpy of vaporization, your standard entropy of vaporization, and heat capacity at constant pressure. So these are the chemical properties. All these chemical properties are, or we can say that can be predicted from some your regression line. Okay. So the model equation is, see that equation number 6. No, this is equation number 6. So P means the chemical property or physical property of any chemical compound equal to M into Ti. Ti means topological index plus C. So M and C are the parameter or constant. So based on some given experimental data, we can fit this kind of your regression line. Means we can determine the value of M and C, and then we can predict the similar property for other kind of chemical compound. Okay, so this is a octane, C8 is 18. So this is the one particular representation. So when n equal to 8, that means C8 means n equal to 8. So for n equal to 8, there are multiple your isomers. Okay. When n is increasing, I have already mentioned, when n is increases, the number of isomer will increase highly, exponentially increases. So this is octane. So its one representation is this one, the straight line basically, and another representation is the one. The first one is same as the previous slide, and second one is another isomer. So there is a name. See that there is a name in top right side, 22, 2, 2, 4, then something is written. So big name are there for different isomer. It has different your names. So octane and one of its isomer. This is the diagrammatic representation. And here we have listed say several. I forget actually how many isomers are there here. It is around 15 like that. So all these your isomers for different isomer, different representation for the same your chemical formula. Okay, for the same chemical formula, there are multiple isomer. For the several isomer, we have calculated the experimental data, or that researcher collected the experimental data. This table shows the actual value, actual experimental values. So based on this value, he fitted this, another tables are there. So based on this value, he have fitted 3 regression line, one for A's, for entropy, second one for ascending factor, a third one is for your enthalpy, standard enthalpy of evaporation. Okay, so he has fitted 3 curves, 3 straight lines. See that the A is equal to some constant minus ND1 into some constant. Okay, second one, see that ascending factor equal to some constant minus ND1, same topological index into something. So these 3 equations he has fitted in his paper, and correlation coefficient also calculated. I have not mentioned here. So among these your fitted curves, see that there are 3 diagrams. So first diagram is for your S. First diagram, S is written is vertically. Second one for ascending factor, or third one for your standard vaporization. Okay, enthalpy. Sorry. So among these 3 your diagram, see that the medial one, ascending factor, see that the almost all the points lie on a straight line. No, almost all points lie on the fitted curve. So from this diagram, we can say that this your formula, that means equation number 8, gives the almost all correct answer for all isomers, because all the points lie on the same straight line. But this is not true for the first diagram and second diagram. The points are certain scattered or deviated from the regression line. Okay, and see that the regression line, correlation coefficient also calculated here. Correlation coefficient for first case is 0.9537, negative, minus is there. Minus means one value will increase, to another value will decrease. Okay, if the value of the independent variable increase, then the dependent variable decrease. For negative your correlation coefficient, and if for the positive correlation coefficient, both the values, dependent as well as independent variable, both the variable either increase or decrease simultaneously. So in second case also see that the correlation coefficient is more, 0.9904, very close to 1. And for third one it is very less, a 0.8414. So for this reason, third diagram, the points are deviated from the regression equation. And using the second index, ND2 index, he has plotted the same data, and he also shows that the correlation coefficient of all these your physical or chemical your parameters, the correlation coefficients are positive. Okay, in the previous, when we are using the ND1, then correlation coefficients are negative. But when we are using the ND2, another a topological index, see that the correlation coefficient becomes positive, means the diagram are just changes. Okay. But here also we see that the result is more fitted when in case of asymptotic factor. Okay. Almost all the points lie on a straight line. And similarly, for ND3, see that for ND3, this is the graphical representation. This is for ND4, and this is for ND5, and this is for ND6. So these are the applications for this kind of your topological indices. For 6 different indices, he has defined based on your neighborhood distance, and he obtains some you are investigating some chemical properties of chemical compound. Okay, so these are the references. Very few references are there, and see that the last 4 references are from fuzzy graph, means the topological indices for fuzzy graph. One of my research scholar, he did his PhD on fuzzy topological index. Fuzzy topological index means the topological index for fuzzy graph. Okay. And these are the, and see that the first one in this page, the first reference is a book written by myself and my 2 research scholars. They completed their PhD. Modern Trends in Fuzzy Graph Theory. This is published by Springer in the year 2020. And if you want to work on fuzzy graph theory, then you may read this book. In this book, we have a very introductory investigation or representation on fuzzy graph theory. Very big, almost 100 pages introductory chapter is there. And in the last chapter, we have mentioned 10 real application of fuzzy graph theory. That one, the first one. First one, the modern trends in fuzzy graph theories. That one published. Not easily available. If you want to, I have a free copy, free soft copy. So if you mail me, then I can give you that. Okay. So that soft copy is available with me, but its price is not much. I think 6,000, 7,000 like that. Okay. But I confidently say that this is a very good book for the introduction of graph theory as well for some advanced your studies. Okay. And thank you very much for your patience. Figure 3. Your number or not? This one. Yes, yes. Now this one, hydrogen suppressed graph. That one, that tree. Yes, rightly you have mentioned. So after hydrogen suppressed or removing of hydrogen atom, that graph is considered as your molecular graph. Okay, and that will be not the molecular graph. That one you are asking. That one is the number of Hardison ages for paraffins or alkanes. There is one step difference. From if you remove the hydrogen atoms, it will be a chemical graph, and if you keep the hydrogen atom, it is called the paraffin or alkanes, the name of the chemical. If there is an next slide maybe. Yes, here. Now, basically this calculation, no, this number of molecular graph of acyclic compounds are trees. This is the one sentence. That sentence finished here. The molecular graph of acyclic compounds are trees. This is the one complete sentence. After that, we have discussed about your alkanes. Okay. So if you have your doubt, then I can remove this sentence from this slide. Then there is no confusion. No, the chemistry people are not working on this area. Okay, nowadays the chemistry has developed lot of development have been done on chemistry. They are working on another things because they have no idea your mathematics. Okay, I have presented this presentation in a chemistry conference. Okay, so some friends of my friends from chemistry departments, they are saying that you are saying some atoms, molecule like that, but we have no idea about your that kind of mathematical expression. So they are not interested, but the winner, Randix, they are chemists basically. They are chemists. They are trying to find out something mathematically. Okay, as per their need, they develop this formula. Mathematician can work this in this area by taking the help of some chemistry people. It will be the good. No chemistry people will work this type of your mathematical works. Okay, they will not interest. You need the chemical properties. No, we have no idea. Mathematicians have no idea about the chemical property. So lot of names I have mentioned, no, entropy, enthalpy, like that. So these are familiar with only the chemistry people. So you need the help of them. Then you can work properly. No, DNA I have not mentioned here. DNA is different. You can analyze DNA using a graph that is known as probe interval graph. Probe interval graph, P-R-O-B-E, probe interval graph. So that graph is used to analyze the DNA. So there is a very one or two fundamental papers are there. After that I have not seen any papers. Okay, probe, P-R-O-B-E, probe, P-R-O-B, B. Probe interval graphs. That graph is used to analyze DNA sequence.
Is there any other question or query, Dr. Pal?
Yes. Mail ID. Okay. This one. Sir, already. Already. When I was the research scholar in IIT Kharagpur, Professor Sharma was the faculty. So from that time, we are here connected. No.
So God has been very kind to me in that respect.
Namaste, sir. He is a good your algebraic people. Like.
So let's give it
Thank you.
to Professor Pal.
Thank you, all of you.
And now it is over to Professor. And so, what is concluding your session or remarks?
Thank you very much for your patience, and we have somehow managed to successfully complete this conference almost through. So we have another session tomorrow, one online session. Professor Sadat from Turkey, his talk is the only thing that is remaining. Then following that, unfortunately, the talk scheduled, physical talk scheduled by Professor Brian Freeberg from University of Minnesota is now getting delayed or almost getting cancelled because he is held up in Germany due to some issues. So I hope that he may get his issue resolved. Even then, he may not be able to come here for this conference tomorrow. Maybe he may come on Monday or Tuesday to visit me, if possible. Otherwise, as per his plans, he will go to Periyar University, Salem, and other places and go back. So tomorrow is the last day of this conference. So for the 5 days, with the God's grace and with the blessings of a big professors like Professor R.K. Sharma, we have successfully completed 5 days. And I am really much thankful to Professor R.K. Sharma for accepting our invitation to grace this occasion. And he has given a very wonderful talk, even though it exceeded the time limit, but everyone has enjoyed it. We are really very much thankful to you, sir. So it is an honor for us that he has accepted the chair the session also. I thank Professor Madhumangal Paul, yes, sir, and Professor AKB Chand, and also Vishnu Pendiala for visiting us for 5-6 days. And it is a really wonderful experience with him. He has shared his knowledge with all of us. And also, I thank Professor Debasis Giri for motivating me to organize this conference. Anyway, tomorrow we will discuss in a few length tomorrow. So thank you very much for your kind patience. Now vehicle is arranged. That vehicle will leave by 5:30 for darshan, temple darshan at Sri Villiputtur Andal temple. The participants who have expressed interest are requested to join. The bus will go and come back. Then afterwards, the participants who are staying in the hostel can plan their return journey tomorrow. Okay, thank you very much.